All right. So, um, if Professor Satyanarayana and Professor Ganesh would indicate to me that we are ready to go, we could begin the meeting.
No
Yeah.
talk.
Dr. Arvinda Mitra is online.
Yeah,
Yes,
yeah,
he
yeah,
is. He
yeah. Let's
is.
start. Let's start, Pranav.
Yes.
Let's start. Yeah.
Yes. So, greetings, everybody, and a very hearty welcome to the inauguration of the Center for Atomic, Molecular, and Optical Sciences and Technologies, CAMOST, or CAMOST for short. CAMOST is a joint initiative of the Indian Institute of Technology, Tirupati, and the Indian Institute of Science, Education, and Research, Tirupati. These two institutions both have strong departments of mathematics and have scholars engaged in advanced studies in humanities, and very robust strengths in fundamental sciences, physics, chemistry, biological, and life sciences, various specialties in engineering disciplines, and developing modern technologies. Ever since the path-breaking works of the likes of Satyendranath Bose, Meghnad Saha, and C.V. Raman, major contributions to AMO sciences, quantum physics, and developments of technologies based on AMO sciences have been made by Indian scientists. Much of this work has been carried out in various universities and research laboratories in premier institutions in India. The Center for Atomic, Molecular, and Optical Sciences and Technologies, CAMOST, is, however, the first center of its kind. Hosted by the IIT Tirupati and IISER Tirupati, CAMOST would grow into it would benefit from a unique atmosphere consisting of young students straight out of high school and also graduate students engaged in higher education, and of course postdocs and faculties who are engaged in frontier research. We are very privileged today to have with us to inaugurate CAMOST Dr. Arvind Mitra, Scientific Secretary in the Office of the Principal Scientific Advisor to the Government of India. Thank you, Dr. Mitra, for joining us. CAMOST comes into being. CAMOST comes into being, of course, due to the visionary leadership of Professor K. N. Satyanarayana, Director IIT Tirupati, and Professor K. N. Ganesh, Director IISER Tirupati. They recognized the confluence of science, engineering, and technology in Tirupati and guided us in setting up CAMOST. I now invite the two directors to deliver their address. Professor Satyanarayana first. Professor Satyanarayana.
Yeah, thank you, Professor Deshmukh. Uh, First of all, welcome to all the participants. Most importantly, welcome to our chief guest, Professor Arvind Mitra, and the Scientific Advisory Council members who have graciously agreed to guide us as we develop the center, and faculty and staff from both IIT, IISER, and various sister institutions in India and abroad. This is a very, at least for me, a dream come true when IIT Tirupati and IISER Tirupati started way back in 2015. Now this was a great opportunity for both institutions. The first time in the country that an IIT and IISER were coming up in the same city. Not only the same city, very close to each other. We are on the same road, just 3 kilometers apart. And we had even a common foundation stone laying program on March 28, 2015. And we started our academic programs in the first week of August, both just a few, 2-3 days apart. So we've been walking hand in hand from the beginning, and I came in as a professor in charge because IIT Madras was mentoring IIT Tirupati, and I was sent in to get things started off. And Professor Ganesh was then the director of IISER Pune, and IISER Pune was mentoring IISER Tirupati. So as a mentor director, he was here. And it so happened that both of us ended up being directors of these two institutes, respectively, subsequently. So we started talking from the very beginning. The moment I got appointed as professor in charge and it was identified that ISO Pune will be the mentor institute, I called Professor Ganesh and said, you know, we need to do a lot of things together and leverage this advantage of the country's premier technology institute and the premier science institutes coming up close by, and we should complement each other's strengths and see how we grow. And so subsequently, as we've been growing, we've been working with each closely. And you know, one of the things that we did is to bring in early some very senior faculty members in setting up these institutions. And for example, at IIT Tirupati, initially we brought 5 senior professors who had just retired from IIT Madras, IIT Kanpur to come over and guide us. And this move, I think, at that time, someone was cautioning me, bringing too many senior people at the beginning are you sure you want to do it? But let me tell you, it was only because we did that, we were able to do these kinds of things. And Professor Deshmukh, and of course, I go back together to IIT Madras as faculty members. And, you know, my first interaction with Deshmukh was, I used to be professor in charge of alumni affairs at IIT Madras. And Professor Deshmukh was head of physics, and he had this passionate idea of building a cyclotron with the students' participation. So he approached me at that time, I'm talking about 2007-8 period, to see if we can get alumni funding to do this. And in fact, I set up some meetings and so on. It was not successful. But what I found that he consistently followed up on that, even after that, after I left, and he did not leave it. And so when we came here, and started this institute, and we started our faculty hiring, and you know, and Professor Deshmukh started these various activities, bringing in workshops, conferences, hosting the 7th topical meeting of the Indian Society of Atomic and Molecular Physicists, and brought in a number of these people working in the atomic molecular area to the institute. And many of these events were pulled across IIT and IIT and ICER. And I started talking to them. I'm basically a civil engineer. I don't know enough of the physics behind it, but when we started hiring our faculty members, suddenly we realized that we had a critical mass of young, enthusiastic faculty members between our 2 campuses, almost 7 or 8 of them, working in the AMO physicist area. And we had people like Dilip Angam and Professor Stefan, and few of these people, Professor, you know, we've been in touch with Professor Krishna Kumar, Steve Manson, Dr. Ravindra Kumar, and all these people. And, you know, they said, you guys have a critical mass of young faculty members at IIT in Tirupati, between the 2 institutes in this AMO areas, and probably this is will become the biggest group in the country. So that's when, and then you had the mentor in our guru and guide, Professor Deshmukh, who you know, brought this group together and has been in touch with the experts across the world. You can see from the Scientific Advisory Council that he has put together people from India, people from going from Japan all the way to US and Europe and so on, and the best people to guide us in taking this forward. So we had planned on starting this, inaugurating the center sometime in the around the first week of April. And we have been in touch with Professor Arvinda Mitra to inaugurate this. He was supposed to come here, and then all things went haywire with the COVID-19 pandemic. But then we said we need to get started. So let's do an e-inauguration and get going. And both the institutes have committed some seed funding to fund research in this particular area to get the essential equipment. And recently, when they call for the technology innovation hubs under the National Mission for Interdisciplinary Cyber-Physical Systems came up, we were initially considering applying under quantum physics, but then we later on changed it to positioning and precision technologies. And I'm very happy to tell that we've been selected, for an institute that's barely 5 years old, to get selected for a national center. I think is a good achievement. And we will be, and then in that we have when we recasted the proposal moving from quantum sciences, quantum technologies to the positioning and the precision technologies, we brought in a lot of those quantum related issues into this, including atomic clocks and related various technologies. So we'll be the national hub for these technologies in the country. And of course, we are going to have linkages with various institutions. I know ISA Pune got the National Technology Hub for quantum technologies, so we'll have strong linkages with them. And we have already started talking to institutions like I can see Professor Bhattacharya is here, Professor Mohandas are here. So we have initiated discussions with them. They're setting up an institute for quantum technologies at the Chatterjee Group Trust institution, and we're talking about offering joint courses, joint. So we're starting to create linkages. So I see a great opportunity, potential for this growth, and our joint collaboration with ISA. This is the first of these centers. The next center that we're going to launch, the joint center, is a center on energy, and so on. So we see this Tirupati becoming a major hub for promoting these technologies. So once again, thank you all for joining. As I said, I'm a civil engineer. I don't know enough. I don't want to talk the science part of it, which is all the experts are here to talk about it. So thank you everyone for joining us and blessing us and guiding us on taking these centers forward. Thank you very much.
Thank you, Professor Satyanarayana. Let me invite Professor Ganesh to deliver his address. Professor Ganesh.
Thank you, Mr. Deshmukh. Dr. Arbinda Mitra, members of the Scientific Advisory Council, expert members, the adjunct members from other institutes, PIs from IIT, IISER, Professor Satyanarayana, Professor Deshmukh, faculty from ISER and IITs, and other distinguished invitees. On behalf of ISER, let me welcome you all for the launching event of CAMOST. The anagram CAMOST, coined by Professor Deshmukh, stands for Center for Atomic, Molecular and Optical Sciences and Technologies. This is the first joint initiative by IIT and ISER among the many that we have been planning. As it was mentioned, Tirupati is the only city where there are two institutes of national importance, IIT and ISER. It provides an excellent opportunity for the two institutes to harness the young talent in both science and technology to create advanced centers for research in challenging and desired areas. The areas covered under CAMOST not only have significance and challenges in terms of basic sciences, but also the scientific developments in these areas are going to have wide impact on emerging area of quantum technologies and in practical applications in health, communication, metrology, navigation, space, internet, etc. The vision and mission of CAMOST is clearly defined, which reflects the challenges and goals. Though at present, the topics chosen are based on the present expertise available, it would be expanded further, keeping in mind the global challenges and requisites, and it would even prompt the two institutes to look for future faculty in the gap areas in expertise. Broadly, ISER expertise and interests are currently in astrophysics, astrochemistry and atmospheric sciences, and optical tweezers for biomedical applications, while more technology-related aspects are covered under with IIT Tirupati, like ultrafast physics, quantum dynamics on attosecond timescale, quantum communication, quantum technology and applications, etc. Quantum chemistry and statistical mechanics both have converging strengths in both institutions. It is good to see the combined strengths of the two institutes covers the critical areas of quantum-related technologies and has a nice synergy. The Scientific Advisory Council with international experts, national and international experts, clearly reflects our desire to be at the global edge, while the adjunct members from other premier institutes reflect the desire to seek collaboration in areas to broaden the scope of the center, including collaboration with other Indian institutions. In a preformed format, the combined group of faculty has already organized jointly an international conference and held deliberations and workshops in this area. Later on, you will see some glimpses of research initiated under the center, including participation of undergraduate students from both institutes and publications. We are also introducing joint undergraduate and PhD courses in atomic and molecular and optical sciences with the institutions. The students can share credits among the two institutions. Though initially the two institutes have pooled in internal resources, the center would compete for national and international funds. In this context, I'm happy that Dr. Arabinda Mitra from Scientific Secretary to Principal Scientific Advisor's Office is participating in this meeting, in fact, inaugurating the event. The Office of PSA, as all of you know, identified areas of futuristic science and those critical for nation's development, and DST is developing mechanisms for selection of the proposals for funding in these areas. Quantum technologies are one of the recommended areas, and CAMOST should be able to compete for funding under this program. Finally, I would like to place special appreciation for Professor P.C. Deshmukh, who has passionately guided the young faculty with great passion for establishing the center and will continue to guide the center both academically and administratively. Thank you, Professor Deshmukh. I also thank all the scientific advisory group and adjunct members from other institutes for their acceptance to be part of the center, guiding and mentoring the faculty. I'm sure they will also be active collaborators. This is our first joint venture between ICER and IIT, and the future ones include in the areas of energy, data science, and even establishing common high-end analytical and research facilities. IISCR and IIT would provide a new model for institutional collaborations, and we have the advantage of being neighbors. Before I conclude, just a few words about ICER Tirupati. Now we have about 50 faculty. We also started in 2015, as mentioned by Professor Satyanarayana. We have almost the same date of birth. We have about 50 faculty together in chemistry, biology, physics, maths, and earth sciences. And we have at present about 650 students, including about 65 to 70 PhD students, and about 30 postdoctorals, 45 integrated PhD, and 500 BSMS students. Our first batch of students, BSMS students, who joined us in 2015, about 35 in number, are graduating. And I'm happy to tell you that our convocation, which will be an online convocation, is scheduled on 26th August. And Dr. Kasturi Rangan, who is the architect of National Education Policy 2020, will be the chief guest. So with this brief remarks, I wish the center all the success, and thank you very much.
Thank you very much, Professor Ganesh. And certainly the guidance and support that we got from both the directors has been the very basic reason why CAMOST comes into being. I recall with great satisfaction and much pride the contributions of a good number of AMO scientists over a period of well over a decade who recognized the importance of having a national resource of the kind that we are trying to set up at CAMOST. In particular, I will like to mention stimulating discussions with Dr. K.P. Subramanian, Professor E. Krishnakumar, Professor Lokesh Trivedi, Dr. Tapan Nandi, Dr. Bhas Bapat, and many others, including Dr. Safwan of the Inter-University Accelerator Center in Delhi. Dr. Safwan is also the current president of the Indian Society of Atomic and Molecular Physics. We are honored to have Dr. Safwan with us at this meeting, and he will tell us about the origins of CAMOST. Dr. Safwan.
Thank you, Professor Deshmukh. Dr. Arabinda Mitra, Professor K.N. Satyanarayana, Professor Ganesh, and Professor Deshmukh, and all the other distinguished invitees. This time, at least, I need not say dignitaries on stage. Everybody is at their own places. So it gives me great pleasure to be present here today as a representative of the Indian Society for Atomic and Molecular Physics, of which Professor Deshmukh has been a very active member. And I must congratulate Professor Deshmukh for his relentless efforts to have a Center for Atomic and Molecular and Optical Sciences. It has been one of the wishes of all the members, and he has named quite a few, that there be such a center which addresses purely the atomic and molecular and optical sciences fields. I think the first effort it was initiated during the National Conference on Electron Collision Processes in Vallabh in Gujarat sometime in 2013, where Professor Deshmukh along with K.P. Subramaniam, Tapan Nandi and others made a proposal to set up a national facility. This was supposed to be in Gujarat with the Charutar Vidya Mandir as a joint proposal, but it did not work out due to logistics and priority mismatches with educational institutions, private educational institutions. Then I remember there was an attempt to set one up at the Gyan Bharati campus in Bangalore University with Professor Bhanudas. And also I remember that while P.C. Deshmukh was stationed at IIT Mandi, he also tried very hard to set up a center at some place. He was looking for a home. In IIT and IISER Tirupati, there has been a providential confluence of favorable circumstances. First, of course, the presence of P.C. Deshmukh, then the large number of AMO faculty that have joined the two institutes, and last but not the least, guidance and support given by K.N. Satyanarayana and Professor Ganesh, which I have seen when I was there for the topical conference, which was organized by IIT and IISER in 2018. And I remember that the synergy and cooperation of the young faculty was appreciated by all the members of the society during that conference. So the formal proposal was made at a meeting in IIT Tirupati on 20th March 2019, where Professor Dilip Angom from PRL Ahmedabad and E. Krishna Kumar, presently at RRI Bangalore, we met along with what they call the core faculty of CAMOST, and prepared the proposal. I'm very happy that it has now come to the stage that I can send my best wishes to the core faculty of CAMOST and hope that they continue to demonstrate that the idea that such a center was justified, right? And encourage collaboration within the country and abroad. And as they say, the proof of the pudding is in the eating. And so I would congratulate all the members of CAMOST and especially Professor Deshmukh on this setting up of this. Thank you.
Thank you very much, Dr. Safan. Along with Professor E. Krishna Kumar, Professor Dilip Angam, and Professor Manson was also present at that meeting. Your recommendations have come a long way, and CAMOST comes into being because of your support and advice and guidance. Dr. Arabinda Mitra has made towering contributions to the science and technology program in India. He is a distinguished geologist, geochemist, geophysicist, all in one. The scientific programs he launched include those he did in the Antarctica. He served as Indian representative to the international treaties on Antarctica. Dr. Mitra established low temperature ice cores study lab. Dr. Mitra leads science and technology innovation projects involving cooperation between very many countries. We are very fortunate to have you, Dr. Mitra, to inaugurate CAMOST. And as a mark of this inauguration, we will request Dr. Mitra to release a brochure which the CAMOST faculty has produced, and also a video documentary which has been prepared by our colleagues at CAMOST. So first, after Dr. Mitra will announce the release of this, our technical support will flash the first page of the brochure. So Dr. Mitra, may I request you to please announce the release of this brochure.
Thank you, Dr. Deshmukh. It's my great pleasure and privilege to release the brochure of CAMOST.
Ravi and Shrikant, will you flash the brochure? Yeah, this is just the first page of the brochure. It is a small brochure which has been produced by all the principal investigators in CAMOST. It has some 19 pages or so, and we will be uploading it at our websites soon after this inaugural meeting. Dr. Mitra, I request you again, as a mark of inauguration of CAMOST, to please release the video documentary which has been produced by the CAMOST principal investigators. Dr. Mitra.
Thank you so much. It's again my great pleasure and privilege to announce the release of the CAMOST video. Over.
Yes, Shrikant and Ravi, will you play the video documentary? It should come up in just a moment. Shrikant?
1 second,
Ravi?
sir.
Yes, sure. I don't hear the audio, Shrikant. I see the images, but not the audio. Shrikant?
1 minute.
Yes, okay. Maybe you want to play it from the beginning. Once you get the audio feed, please start it from the beginning. Jointly hosted the 7th topical meeting of the Indian Society of Atomic and Molecular The twin townships of Tirupati and Srikalahasti are spaced merely 40 kilometers from each other. Between them are growing rapidly our two institutions, the Indian Institute of Technology, Tirupati, and the Indian Institute of Science, Education and Research, Tirupati, set up together in 2015, foreshadowing Tirupati's resolve to emerge as a major hub for sciences and technologies, pushing the very edges of their frontiers. The IIT Tirupati and IISER Tirupati jointly hosted the 7th topical meeting of the Indian Society of Atomic and Molecular Physics on January 6, 7, and 8, 2018. So this is the first conference that we are holding, and maybe it's also true with IIT perhaps, the first major conference that we are organizing, and of course together. And I hope all of you will enjoy the science part of it. It's a great opportunity for our two institutions to work together, as Professor Ganesh has pointed out. We've been, trying to leverage each other's resources, strengths, and how to take things forward, and we see it as a great opportunity. At a meeting held on 20th March last year, leading AMO scientists in the country and a number of young scientists from several institutions in India recommended the formation of the Center for Atomic, Molecular and Optical Sciences and Technologies, CAMOST, to be jointly hosted by the IIT and IISER. Focal areas of research undertaken currently at CAMOST include ultrafast physics, quantum dynamics on the attosecond timescale, quantum communication and quantum technology applications, quantum photonics, cold plasma applications, laboratory astrophysics, astrochemistry, and atmospheric sciences, optical tweezers, single molecule force spectroscopy of macromolecular systems, single molecule magnetism in organometallic complexes, quantum chemistry, statistical mechanics, and high technology devices. Our research group focuses on fundamental
atomic, molecular, and optical physics research using cold-trapped atoms and cold-trapped ions. In particular, we are interested in developing translational applications of quantum technologies in communication, sensing, and metrology. In the laboratory astrophysics group at IISER Tirupati, the physics and chemistry of interstellar medium and also of the Earth's atmosphere is being studied using both experimental and theoretical techniques. A versatile experimental laboratory is being set up, featuring a cryogenic multipole radio frequency ion trap, which is currently under construction. Plasma processing lab at IIT Tirupati is involved in doing research to utilize non-thermal plasma technology for wastewater treatment, cancer diagnosis, agriculture, and food processing. We also carry out fundamental studies to understand plasma surface interaction. Ultrafast Quantum Dynamics Group at IIT Tirupati studies theoretically the interaction of strong and ultra-short laser pulses with atomic and molecular systems. We develop new manipulating techniques and employ them to analyze use attosecond spectroscopic techniques. In the Excitation and multi-scale computational chemistry group at IISER Tirupati, our primary interest is to explore light-induced properties of organic chromophores and transition metal complexes for biomedical and material science applications. Our group is currently exploring different quantum space systems using theoretical spectroscopy. We study water dynamics under the influence of several surface and interfaces. We also investigate structure, dynamics, and biological properties of different metalloproteins. Our lab at IISER Tirupati is primarily interested in studying molecular phenomena at a single molecule level using infrared laser-based optical tweezers. The results are expected to have high implications in drug discovery and medical diagnostics. A significant area of interest in our research group is that of computational astrochemistry. Here, we seek to understand the interesting physics and chemistry of the molecules existing in the interstellar medium. As part of it, we apply electronic structure methods and also develop them as and when required. The vibrant atmosphere in which undergraduate and graduate students work along with postdocs and competent faculty provides an unparalleled opportunity at CAMOST. CAMOST also benefits from the experience and leadership of the members of its Scientific Advisory Council. CAMOST would undertake frontier research and conduct regular seminars, webinars, workshops, and conferences, creating opportunities for AMO scientists, engineers, and technologists to come together to seed and nurture frontier collaborative research in many fundamental and applied areas, including interdisciplinary fields.
Thank you very much, Dr. Mitra, for releasing the brochure and also releasing the video documentary as a mark of inauguration of this center. I am very honored to have the privilege of now requesting you to deliver your inaugural address. Dr. Mitra.
Thank you, Professor Deshmukh. Thank you very much indeed to both the directors, Professor Satyanarayana and Professor Ganesh, for inviting me to preside over this function and to inaugurate CAMOST. Unfortunately, you know, I was expecting to be there physically, and we have been planning to do that almost sometimes from last year onwards. But as it would have been, COVID came in between. But nevertheless, you know, I am glad that this function is happening, even though virtually. But certainly, you know, this would lay a seed and a foundation to a great partnership. I am sure as soon as the COVID gets over, I'll get an opportunity to be physically there once again and visit the two exciting new institutions that have come over the last few years into existence, and to see the progress that they have made, which I could see, of course, over the short video clip. I must say that, you know, the pandemic has actually made us learn many things. And one of the things which the pandemic has made us learn is today, all countries, all institutions, every one of us need to build very strong collaborations and partnerships. And it is inevitable that without these partnerships, we will not be able to meet the challenges which the globe is going to face. And this is very evident. And these collaborations and partnerships also really creates miracles. Now, I wouldn't be the one who would actually promote and preach this, you know, so because it's so close to my heart, being one involved in international SNT collaboration for years, since my days in Antarctica. Somebody recalled it. Thank you. That collaboration and partnerships is the way ahead now. There is no doubt about it. Collaborations at the subnational level, collaborations and partnerships at the national level, collaborations and partnerships at the international level is going to be the actual, you know, way forward from here. And why I say so, you would realize today that it is important for us to leverage our strengths in knowledge, our strengths in infrastructure. No nation alone can actually provide answers to these, multifaceted questions, and therefore it is inevitable that we link with each other and in a seamless way work. And CAMOST is a great example as to how two institutions, in a place has joined hands right at the very inception stage itself. In the Office of PSA, of course, we've been doing several activities, and one of which may be directly relevant is the fact that we are now setting up what is called the city R&D clusters, where we are bringing together the entire ecosystem that is in a city and a region to be seamlessly connected through various processes of collaborations that would then make them as a powerful house or a tool to actually come forward to work in a way through leveraging their existing resources and their manpower and their knowledge. And in the city clusters, we hope that all R&D institutions, national laboratories, state laboratories, the national institutions like IIT, ICERs, the state universities, the entire enterprise in that area, including the industries, including the startups, and also, of course, the local and state governments. They all come together, pool resources, and try to actually address problems which are local, which are national and international in nature. And to that extent, I believe the setting up of CAMOST is a great beginning, and it will slowly seed into actually building partnerships both at the regional, national, and international level. The origin and the establishment of CAMOST, I would say, is very, very, very timely. And I would say why it is so timely, because I would allude upon a few minutes on the major national mission. It is called the National Mission on Quantum Technologies, NMQTA, which is being launched. It is in the state of preparation. And I happen to be a part of the expert committee, rather I would say advisory committee, in defining, currently in the process of making the detailed project report of the quantum technology mission. Now, this is a very ambitious mission, and you would recall that in the last budget speech, the finance minister announced the setting up of a quantum mission at a cost of 8,000 crores. And we are working, therefore, led by the Department of Science and Technology, to develop a detailed project report in order to leverage this quantum revolution which is underway, wherein the growing ability to control and manipulate quantum mechanical phenomena at the level of single atoms, photons, etc., are leading to the emergence of a whole range of powerful new quantum technologies. So the whole purpose of this mission and the DPR, therefore, with a very ambitious vision of the government in having identified quantum technologies as a priority area with the funds that are available to actually launch this mission in a very short while from now. I believe in a couple of months' time, the detailed project report will be ready, followed by the process of financial approval. And I hope by the end of the year, we will have the mission up and running. So I'll briefly tell you the broad outlines of this mission, though it is still at the formative stage, but I have perhaps the access to the outline, which I can certainly share with you as you also develop your roadmap in terms of planning the strategy in your own scientific programs. So as we all know, the relentless drive pushing technology and particularly electronics to ever smaller scales have enabled the rise of information economy that defines the modern age. And quantum technology represents the next frontier in the logical progression of exploring the world to be very, very small. It is anticipated to be a significant driver of economic progress in the coming decades, while at the same time conferring strategic and tactical advantages to nations that are able to establish leadership and preeminence in the generation of new knowledge in the quantum frontiers. NMQTA, which is the National Mission on Quantum Technology, is very much the need of the hour to keep India in the reckoning as a significant player when it comes of taking full advantage of the economic prospects, strategic superiority promised by the quantum technologies. There are, of course, considerable challenges and handicaps that we realize we have in the country, but the vision and the potential dividend that this mission is going to be giving to the nation cannot be underscored. It is very, very compelling. Leading nations of the world, as you know, have recently started investing heavily in promoting this branch of research and development. And NMQTA is positioning India as an answer to these flagship programs, conceived to ensure that we do not fall behind in this critically important avenue of progress. The activities envisaged under the mission will provide a great fillip in terms of invention, generation of new knowledge, invention of new products, services, and creation of skilled human resources at all levels, right from technicians to researchers to scientists to academicians, and of course, entrepreneurs, and would become a key contributor for realizing the national goal of building a 5 trillion economy that we are planning to achieve. Apart from the central R&D themes under the NMQTA, the mission is anticipated to produce several spin-offs and development of peripheral industries, like in the field of programmable gate array-based electronics, micro-machining, nanofabrication, some of which you're already working, that would further boost the returns of the mission, adhering to Make in India strategy. The thrust areas of the national missions are categorized in 4 verticals for effective mission management, administration, and evaluation of progress. These are quantum computing and simulations, number 1. Number 2, quantum communications. Number 3, quantum sensing and measurements. And finally, quantum materials. Synergies between these thrust areas have to be explored and developed as we start, progressing on this mission. Development of human resources, of course, is a major part of the mission, in which I think both ICER and IIT will play a very, very important role. Several mechanisms are identified for implementation so that large pool of trained personnel in the broad fields of quantum technology can be built up rapidly, and this would therefore involve very strong international collaborations. We believe that this is an area which we need to leverage quickly to have faculty and students get trained abroad, and as well as have faculty and students from abroad coming and residing in our institutions to build up human capacity in a very rapid manner. This will enable, cornering the high-value jobs also in the anticipated global market in quantum technologies and related fields. So HRD initiative will be a very, very important aspect of this mission. Since the field is also very nascent stage, the full scope and impact of possibilities offered by the development of quantum science and technologies cannot be comprehended at present. Ways of identifying these avenues quickly and flexibly by focusing resources and attention will be built in the management structure, which is going to be very dynamic, which is going to be evolving one. And we are making sure that in the notes that we put up to the cabinet for approval, we have this ability not to be bogged down by the overall rules and regulations of the government, so that we are able to be nimble and flexible as we implement this strategy. And at the center of the management strategy is a special purpose vehicle that we are putting. This is something new concept which I really wanted to allude to and highlight. A special purpose vehicle named the Indian Institute of Quantum Technology, IIQT. And the IIQT will have a hub and spoke model. Now, these hubs will actually constitute of centers which are geographically dispersed all over the country. And I could see that Tirupati could emerge to be one of such centers already with the existence of the CAMOST. And once the identification of the hubs are made, the hubs in turn will connect with all other institutions around it. And this would, of course, include national institutions, national R&D labs, the universities, central and state, and very importantly, the industries. Mark my word, industries. This is something that perhaps I would allude to later on as I close. These hubs will actually be given a block grant with complete flexibility in terms of how this money is to be utilized within the spoke and the hub, so that there is minimum interference from the government and from the government rules. Of course, we will lay down a broad set of rules for all these hubs, but there will be enough flexibility and nimbleness for the hubs to work. For example, even hiring people at industry level salaries within the mission is just one example that I'm quoting, number one. Number two, the hubs will have full flexibility to provide funds also to industries where projects could be led by industries in partnership with academic institutions. The reverse would also happen, but this is something new that we are adding to this. So we hope, each of these hubs, of course, would identify some of the important niche areas in terms of their research focus, in terms of their technology development, in terms of how they would integrate what I call education, research, and innovation. That is knowledge dissemination, which you call as education, knowledge creation, which is research, and knowledge application, which is innovation. And this is very important as you develop CAMOST. Keep in mind that you have to integrate these three verticals, which should not be kept separate from each other, which is actually the research, education, and innovation. It's important that the research that we do, the new knowledge that is created, is also actually converted in terms of knowledge consumption. In other words, what we would like to see is basically, while we keep on investing in creating new knowledge, some of the knowledge should also be able to generate wealth. And therefore, the need for technology development and application, or the knowledge consumption, should be a very, very important facet of all the hubs and the spikes and the spokes that we would develop in this national mission. And for that, as I told you, all possible administrative, all possible fiscal, all possible governing flexibilities would be provided to make this seamless connect happen. And this is very, very important. So, we know that the markets also have high expectations of quantum technology, and this is very important. Please keep in mind, the research predicts that over the next 20 years, the market for quantum technology will grow to more than 65 billion US dollars. And by 2050, the global market is likely to be worth 300 billion US dollars. Parallels have been drawn with the semiconductor industry. Quantum technology is at the stage of development that semiconductor technology was in their 50s. The ultimate social and economic impact of the quantum technology is potentially comparable to that of semiconductor technology, in which we missed the bus, and we don't want to miss the bus now in the quantum frontier. Certainly when the effects of possible spin-offs to other fields are also taken into account. Strong engagement, therefore, with industry, nurturing a vibrant startup ecosystem, promoting prototype and product development, facilitating broad-based innovation in quantum technologies are facilitated prominently through a gamut of special programs which will be included in the detailed project report as a part of this mission. These ensure that the economic and commercial potential of the research and the new knowledge that is created in our academic atmosphere becomes an integral part of the mission in the country that can be exploited fully for serving the best interests of the country, both in the strategic as well as non-strategic sector. Now, I must, of course, here mention that in the DPR formation, we are doing an extensive consultation across with the academic setup, with all the ministries of the government, which includes the defense, the atomic energy, the space, the IT, of course, biotechnology, and so forth and so forth. All these players are actually brought in together, and each of them will have a role to play in supporting this quantum mission. So to end, I would say that the NMQTA is actually intended to position India as a world-leading center in quantum science and technology. And that is our view. The way, as I told, we need to move forward is through a consortia approach. Most of the projects that you would fund across will have groups of institutions that bring, a wide spectrum of their expertise, because you would agree this is a very multidisciplinary area. Multi-institutional participation is key to this, and I think very rightly CAMOST is actually seeding this. I find that this is a very timely and topical initiative. As I said, as you need to do is to actually expand this partnership, make sure that you bring industries, and also build a vibrant startup community in the IIT and the ICER innovation ecospace. The incubators that you built up, they all get linked, and young students, should be nurtured in terms of actually spinning out technologies and companies out of this massive effort in terms of the new knowledge that you would generate in this setup. So I think if you keep these broad parameters in mind, I think you would really be able to, I would say, leverage three other major missions that already have been launched. One is already launched, and you've got already connected with it, the cyber physical mission. The other mission that is very shortly getting launched is in the final stage of clearance at the highest level of the government, is the AI mission, the artificial intelligence mission. That would be a separate mission worth about 7,000 crores again, that would be rolled out shortly. And of course, the supercomputing mission. So we would like to see that these four large missions, the National Quantum Mission, Quantum Technology, the National Cyber-Physical Mission, the AI mission, and the supercomputing mission, they all get integrated, and there is a flow from one to another, and we should be able to leverage the fundings and the groups that we have created in a copious and a seamless manner through our cooperation to achieve the end goals of this particular mission. I think I would wish this effort all the success. As I told, any help, any advice that you would need from the PS's office will be most forthcoming. Please keep in mind that partnerships and collaborations are way ahead. you must connect with all your international partners whom I see who are there today, part of your scientific advisory committee. They would bring a lot of wealth, a lot of value in what you would do. So build this relationship, as I told, both at the national and international level, which is going to be very, very critical. So I think all the opportunity is there. It's the right time, and it's totally up to you people to actually now work in a collaborative manner to leverage these great missions that we are launching through your support. We of course need your support, your collaboration, and your partnership in making this happen. And in the systems, we are trying to make them as much nimble so that this happens quickly without getting too much bogged into rules, regulations, and bureaucracies of government. So thank you very much indeed. It's been a great pleasure to see many of you whom I know, of course, personally also for long years, like Savan, Bhanu, of course, many of you here. I someday hope that sooner we'll be able to visit Tirupati to see this happen myself. Thank you once again and all the best. God bless.
Thank you very much, Dr. Aravinda Mitra.
Thank you.
We were very keenly looking forward to your visit to Tirupati, and the pandemic has come in our way, but I'm sure that as soon as we get over this hurdle, it would be great to have you with us, and we certainly look forward to having you and spend some time with us. Thank you also very much for your very inspiring inaugural talk, and for showing us the way. You have given us a heads up and tremendous guidance about the way forward. The program on the National Mission on Quantum Technologies is, of course, a very challenging one. It's a great opportunity. And there are young scientists over here, and I'm sure both the institutions, IIT as well as ICER, would recruit more talent, because this is a huge challenge in front of the country, and we need the best people from all over the world to come here and support this activity. So you've given us a tremendous lead guidance in this, and it is very nice that the mission will also involve partnership with industries, with focus on knowledge creation, dissemination, innovation, and end use for the benefit of the society. So thank you very much, Dr. Mitra. I would like to move on to the technical talks which we have scheduled. There are just a few. Yes.
I think Dr. Mitra has another engagement at 5 o'clock.
Okay. Yes.
So he had requested that he be excused. So thank you very much, Professor Aravinda Mitra, on all our behalf for gracing this occasion and giving us insights into the future opportunities. Thank you very much. Look forward to your continued support.
We will be in touch. Thank you. Bye-bye. Bye-bye. All the best.
Thank you very much, Dr. Mitra. Goodbye for now. Okay, so we have technical talks, and AMO sciences are at the very foundation of several interdisciplinary areas. And we have the first talk by Professor Lokesh Trivedi on atomic collisions with Miso Nano biosystems. Professor Lokesh Trivedi. Lokesh.
Yes.
You will be sharing your presentation, and our
Yes.
technical supports team will be assisting you in this.
Okay, I think the slides are visible.
It's coming up, yes.
Okay.
Yeah, so you can go full screen. Yes.
Yeah. Okay, if I go full screen, you may not see my. Yeah. Okay, so you can see my slides, and also you can see my cursor. Cursor is visible or not?
Sir.
Yeah.
Okay.
Yes, sir.
Okay, very good. That's great. All right. So first of all, congratulations to Professor Deshmukh. And I must say that if winter comes, can spring be far behind? So if Ganesha and Satyanarayana, Professor Ganesha and Professor Satyanarayana joins, Professor Deshmukh has taken full advantage to do this CAMOST. So on the outset, I must say, we care most for CAMOST. Okay, so with these words, I would like to start my technical talk. Of course, I'll try to go a little more broad. So atomic collisions are very well known for single atoms, molecules, and so on for many years. But of late, the latest thing is the meso-nano biosystems, which are basically large molecules of different types. And that gives us a glimpse of interdisciplinary science. And to do this, the weapons what we have in Arabian Sea, an electron accelerator, high energy, so-called high energy accelerator, and we have developed our in-house ECR ion accelerator, which is low energy accelerator. So collision studies with meso-nano biomolecules for us, it comprises these two circles you can see. One is, of course, we start our benchmark system, which is C60 fullerene, and then there is something called C24H12. This is one of the PAH molecule, coronin, which are important for astrochemistry and astrophysics. And these molecules all show the behavior of collective resonances. Then, of course, come water. You cannot neglect water, because water gives you the lot of information and applications for radiobiology. Then I give you examples of two, uracil and adenine. They are the base molecules of RNA and another base molecules of DNA. So collisions of these are a lot of importance in case of radiobiology and cancer treatment, which I'll come a little later. And of course, one last example I'll give you, iodouracil, in which one uracil, one of the hydrogen you replaced by an iodine atom, and then see what happens. So this is a benchmark for nano-inserted nucleobases. So here is the sum of the molecules, which is C60. This is coronin, that is C24H12, and this is uracil. Okay, and this is an example of iodouracil. And you see, this is common between the two circles, because all these molecules in this circle show collective plasmon excitation. And this particular biomolecule also, very recent study of ours, not even published, showing that effect of collective resonance. So one example, I will tell you that if you want to do collision experiments, what weapons you have. So we have weapons. This is an outline of our ECR ion accelerator with different beam lines. And I'll tell you everything, all of it, most of it are in-house development done in TIFR. Taking advantage of excellent facilities in TIFR, we could develop this. So this is the example of an electron scattering setup in which you have a hemispherical analyzer, and we measure electrons and their angular distributions and so on. In another experiment, of course, I am not showing all, we also measure time of flight spectrum and measure their recoil and momentum spectroscopy, that is known as. So just as a basic, when ion comes, it hits an electron and electron is emitted, and recoil ions also emitted, and ion goes. So we try to detect all these electrons, recoil ions, and also the final charge state of the ions. So this is just an example of simple ionization of an atomic hydrogen. Of course, if you go complicated molecules or complicated atoms, then you have inertial processes, which is also very, very important, and many people are involved in these studies. So another mechanism which is involved is electron capture by bare ions, which is like this. So the electron sees the field of the potential of the moving ion and gets captured by the ion. This is an important mechanism apart from fragmentation, double ionization, double transfer, and so on. So this is an example that interference of electron spectrum in a molecular double slit. So that's a relatively newer topic, that double slit means two hydrogens in a molecule are indistinguishable, and electrons show a very nicely oscillatory behavior due to the coherence, that is a spatial coherence. And this is now by this time is well known, and there are series of publications internationally, many groups as well as our group. This is kind of our flagship measurements, and we could show that yes, such interference exists due to the electron has a wave nature. So this comes really a quantum mechanical applications. What we are talking about, quantum technology, can be related to this. Now, when heavy ions passes through, for example, water molecule or DNA and RNA bases, that gives a lot of input for hadron therapy. In hadron therapy, you shine very high energy like GeV energy ion beams like carbon or proton ions in big accelerator centers worldwide, and you remove the cancer. Physics, what happens is here, there is a Bragg peak. That means once it penetrates inside the body, at certain distance, it removes the maximum energy loss happens here, which is called Bragg peak. And if your tumor happens to be here, you can remove the tumor without destroying much of the cells before the tumor. So it is like example here, if you have a photon, it goes through the tumor, but still destroy a lot of other molecules, other cells. Whereas in case of heavy ions, they destroy only selectively the tumor. And that is a good application. But to understand that basics, we have taken up certain measurements. So one very nice example here, Times of India report, city is set to get high-tech proton machine for safer cancer therapy, which has now arrived in Mumbai, some of the hospitals. But basic physics is like when you take a biomolecule, you heat with an ion, you ionize, you fragment, and you lose energy. But how much energy lost, that has to be told by a physicist. And that is why these are one of the very first set of measurement. You can see big difference between experiment, the red line is the theory and best known theory, and these are the experimental data from ECR and Electron. One can see a big difference. Hence, there is a need for actual experimental measurements so that doctors can use for their simulation. Of course, by using more mechanisms like something called transfer and ionization together, then some of the theories could reproduce our data with their theory quite well. So that is very pleasant experience for us. Now, the low energy electrons, these are science papers many years back. Low energy electrons are actually the main responsible for radiation therapy. So they hold the key. The question is how to produce more and more low energy electrons in the cells, inside the body, inside the tumor. So before I go to that, one example is collective excitation. So there is a collective excitation that when ion beam comes, it goes through, for example, C60 molecule, and it excites the C60, and as a result, when it decays, it gives rise electrons. So this collective excitation gives rise a lot of electrons, and this we first made a benchmark study using C60. And here is clear example how collective plasmon excitation gives you huge electron enhancement over the normal line what you have expected from this red line. So much more enhancement, and this enhancement is almost a factor of 2 compared to total cross section. I mean to say it is 50% enhancement due to this itself. So this is one clue, and when we started with this, of course, there is a TD DFT calculation later on done, and which agreed with our measurements after our publications. So now here is an example how to increase this electron density. So you join hand two things. One is nanoparticle and one is biology. So here is a nanotechnology or nanoparticle inserted inside a DNA, and suppose the ion beam passes through that, this nanoparticle is shown or predicted to produce lot of electrons, lot of low energy electrons due to the mechanism of plasmon excitation. Those electrons can go and interact with the rest of the DNA or water molecules and so on, and that gives rise a huge number of radicals and low energy electrons, which will further destroy to the rest of the. So what is the beauty of this technique? By this technique, you can enhance electron emission internally like an amplification, and hence you need to have a lower amount of dosage. Nobody likes to have too much dosage in the body. So by this technique, one can have lower amount of dosage, but large amount of electron emission, hence cancer can be removed or tumor can be removed. However, actual technique wise, it is very difficult and still under progress. So here I give one example what we did, a poor man's system that is nano inserted biomolecule, we took a uracil and put on iodine. It's available. You can get an iodine. So this is called iodouracil. Iodine is a metal atom which, as we know, has a collective excitation mode. So we started this experiment a couple of years back, and now you can see the results here. This dotted, the black dots, black circles are due to iodouracil and red are due to uracil. So this ratio is plotted here, and numbers are important in physics. You see the numbers are typically between 2 and 3, typically 2.5 or so, and at two different angles. So that means what we say here, that 2.25 or 2.5 times enhancement we observe in the electron emission. Now the question is, what do we expect from theory instead of doing such experiments? So best known theory called CDWEIS, continuum distorted wave iconal initial state, let's not go to details, predicts at most 10 to 20% enhancements. So then what we did, we took help of the theory which is based on joint resonances and many electron correlation, which is normally neglected in these models. Once we have a giant resonance and many electron correlation, we find the expected enhancements of the order of 2.0, which is an excellent agreement, our measurements, which is 2.25. And this is just tell you that this is just submitted recently, and we are fighting with some journals, from high-profile journals with this, and hopefully it will be published sometime soon. So this is one example. Another example of collective excitation is celestial bodies, astrochemistry and astrophysics. One always wonders what happens, the UV photon absorptions. So big absorption of the UV photon comes due to this PAH molecule, which is C24H12, polycyclic aromatic hydrocarbon molecule. We did an experiment at the lab, and we can clearly see the 17 electron volt here. It has a mode of collective excitation. Big peak, we could see this. And this was, we could see for the first time, we could show. And then, of course, it agreed with a theoretical model, which is dotted line here. And of course, which you don't see other normal molecules like methane or neon and so on. So this is one example. We could see that collective excitation influence for astrochemistry, astrophysics, as well as biology. So here comes as a recognition. Just a few days back, you see the date, August 7, your research on the EPJ news page. I mean, this was very pleasant. We are very happy to see this, one of our papers on these biomolecules. They write to us, we are pleased to inform you that the synopsis of your article is now available on EPJ News, which is basically news and highlights and colloquia, and they informed us to have a wide publicity everywhere of this kind of work. So this is, as I said before, now here, as I told you before, you need instruments, and we could build a lot of instruments, not one, two. In fact, this is the equivalent of a center, I must tell you. So you have ion source, we have accelerators, we have strong lasers in TIFR, which you will hear soon from Ravi. And so this can drive a whole group, and actually many faculty members. We have ECR ion source, one of the beamline. This is electron spectroscopy chamber. This is X-ray spectroscopy chamber. And this is time of flight spectroscopy chamber with a deflection arrangement, final charge state deflection arrangement. And this is a different view of electron spectrometer. So this is different view, and I must tell you that many users from the country are coming and using our ECR ion source. No committee, no big deal, just an email to me is enough, we give beam times. And this is different picture, like this one of the new development by one of our younger colleague, Dipankar, for the cold target recoil and momentum spectroscopy, a brilliant development here. And this is a backside picture of ECR when we did not enclose it beforehand. So this is now after closing the ECR, you can see this picture. I am showing this because any center, any institute you try to make, there should be a strong instrumentation culture, which will take you for many years and give you access to do different kind of science. So basic mechanisms in collisions with large molecules and cluster I have hinted. I have talked about little bit of interferences, electron transfer and fragmentation, and many electron correlations, which is very, very important and which is generally neglected in theories. Collective giant resonance is one of the major mechanisms to understand biomolecule collisions and any meso nano biosystems. or +1 excitations. And large-scale instrumentation building is a part of the game, particularly for experimental programs. So the accelerators, ion sources, lasers, this I just wanted to give a glimpse that what are required. So these are acknowledgement, my big group over many years, many of the students, and we have a strong theoretical support from country as well as abroad. And we thank all of them, particularly my all student and past member, many of the past students and my colleagues. And TIFR provides enormous facility, central workshop, Electron and ECR team, and all many project students. So here I say that theory support is crucial, which is very important. Any new center, you must keep in mind theory support is crucial for experiment, and theory and experiment must go hand in hand. So here is a picture. Where do you get experimentalists? You know, stormy days now in TIFR. So this is the TIFR garden just beside the Arabian Sea. You can have a feelings of sometimes a stormy day, and we love beside this. This gives you experiment. And of course, theorists, you can catch any conference anywhere in the world you like, either on the sea or on the stones. So thank you all for your attention.
Thank you very much, Lokesh. It was a wonderful talk, providing insights from fundamental quantum superposition, quantum collision dynamics, and its applications in biological systems and so on. Fantastic talk. I'm sure there may be a question or two for which we have time. Any question?
Hello, Lokesh. This is Sunil. Can I ask a question?
Sure.
Okay. So this is regarding the discussion on incorporating the nanoparticles inside the biomolecule, like
right.
DNA, and then in order to generate these electrons, you are having that nanoparticle inside. So, is there any plan by which you incorporate these particles inside the DNA molecule? So, how is it done? Okay.
Very
real application, for instance.
Yeah, very good question. So my answer is, at the first step, we have taken a single metallic atom just to prove of the principle, because the idea was, people thought there will be huge enhancement. So we experimentally showed that enhancement is good, but of the order of limited up to 2 to 2.5. Even if I compare this with water molecule, we have done that, I have not gone into details, is about 2 to 2.5. Now there is only one measurement so far by using a platinum nanoparticle, which surprisingly shows similar enhancement, something like 1.6 to 2.5 in that range. But now let me tell you, the second part is, yes, we do have a plan, but you need a real collaboration with the biologist to do this. It is an extremely difficult experiment to put a really a nanoparticle, what people thought about thousands of gold atom, thousands of particle of platinum atom, put a cluster, put inside the DNA. So we are not doing that right now, but I know worldwide there is a effort to get into this experiment right now. It is going on.
Okay.
But definitely we can also do, based on the experience, we can do. In fact, I'll be most happy to help you if somebody develops there, no problem. Or we can do even here. It's not impossible.
Okay, thank you.
So thank you very much, Lokesh. We are slightly behind the clock, so I think we will take just one question. There will be many other questions which we can forward to Lokesh.
Sure, most welcome all the time.
Thank you very much, Lokesh. And I'm sure the center will have a lot to interact with you and others at TFR.
Yeah, as I told you, I remember 2018 we have an international conference. You started this discussion in the AISM conference when all of us contributed. I'm glad that it has materialized.
Yes, thank you, Lokesh. Sure. So as Dr. Mitra mentioned, AMO Sciences have a strong overlap with quantum technologies. We have with us one of the very important contributors to this field in India, Professor Aditi Sen Dey, and she will talk to us about recent developments in quantum technologies. Aditi.
Yeah, thank you. So, Lokesh, can you stop sharing? Yeah. so that
Yeah,
I can share.
yes.
Yeah.
Yes, your presentation is on the screen now.
Okay. Okay, so thank you very much, Professor Deshmukh, for involving me in this nice program. And I really very happy. I hope that all the best to the center. And I hope that there will be some future collaborations with the people in the center. I have already talked with some people who are involved in the center. And I also hope that I will see in person or will be able to visit IIT Tirupati and IISA Tirupati soon. So actually, Dr. Mitra has given a nice introduction of quantum technologies. So I will present some of our work at HRI on some of our recent works at HRI on quantum, towards building quantum technology. Although I am a theoretical physicist, so the results that I am going to talk about all the theoretical proposal, but I strongly believe that there will be, as our previous speakers said, that theory and experiments should go hand to hand. So it will be important for the, also I hope that there will be collaborations with the center towards building quantum technology. So there are several, over the years, there are several proposals, several developments have been made for building quantum technologies. So one of the prominent one is quantum communication. So quantum communications can be broadly classified into two categories, where one wants to send classical information using quantum state. Another is the quantum state transfer. And classical informations can be sent either with security or without security. When it is sent with security, then it's known as a cryptographic system. Another prominent one is the quantum computer, where we want to build a computer by using the principles of quantum mechanics. I will also talk about some of our recent results on thermal machines. I will show you that quantum mechanics help to enhance the capacity of or the efficiencies of thermal machines. Finally, I will talk about some of our recent results on fundamental questions. And I will show you that addressing these fundamental questions actually help to build some of the quantum technologies. So let's start with communication. So first I will talk about classical information transmission. So classical information transmission protocol goes as follows, that suppose there are a single sender and a single receiver, and sender wants to send some classical informations to the receiver. And this can be the informations about the inaugurations of this center, for example. Now, sender wants to encode this information in a quantum state and send it to the receiver. And it has been shown that if they use quantum mechanics, then the efficiency or the efficiencies of these protocols can be enhanced. So the initial protocol actually involved only a single sender and a single receiver. But as we know from our daily experience that this point-to-point communication has very limited commercial use. So the next obvious or the natural question is how to transmit classical informations where we involve several senders and several receivers. And this was addressed actually long back by us, where we have the following scenario where there are n numbers of senders and there are one or two receivers, and these senders and receivers initially share some entangled states. This is a special quantum mechanical states having some quantum feature. Now this sender wants to encode this classical informations into quantum states. Then the sender send this information via quantum channel to the receiver, and receiver decode the message. Now this quantum channel can be noiseless as well as noisy, Now, if you have a noiseless channel, then this was the classical capacities are found in this paper. But in a realistic scenario, in an experiment, the channel is always noisy. So in that scenario, we have recently addressed these questions and found classical capacities. We also established that even in this multipartite or this many particle scenario, multipartite entanglement will be a resource, and we establish a connection between entanglement and this capacity of the quantum channel. Now, the next goal probably is to build a quantum network, where a network is a collection of nodes which are connected by edges. So we want to communicate informations between these different nodes. As I have told you, that in this communication protocol, entangled quantum states are important resource. And so it's important to share entanglement over large distance or over pre-decided nodes. So recently, we actually proposed a protocol where we show that this kind of building block, where the nodes, this is a single node example, where a node is connected with several quantum states. And if you perform global measurements along with the local measurement, then entanglement of the sharing entanglement in prefix node is easier. In this way, we are able to establish connection between one-dimensional quantum network as well as an arbitrary two-dimensional quantum network. The question that I again want to stress that we want to share quantum resource in pre-decided node in this network, and that is probably the goal of the quantum network. So talking with Arijit at IIT Tirupati, I realized that although these proposals we have done in around 2000, there are other protocol also people have proposed around the world. So I saw that Arijit's lab actually is trying to build this kind of network. So they want to build a hybrid quantum network where there will be an atomic and solid state system can be used as quantum nodes. And these quantum nodes communicate with each other by exchanging single photons. So this is so the protocol that we have given, which is a theoretical protocol. So one can think that this is the initial stage to really build a quantum network. In this quantum network, as I said, photon is the important candidate for quantum communication. So the continuous variable systems like Gaussian or non-Gaussian states are important members for implementing quantum communication. And we also showed that entanglement is an important resource in quantum communication. And we have recently found how to measure this entanglement in case of continuous variable systems. In particular, we show that there can be a non-Gaussian state which poses higher amount of genuine multimode entanglement compared to the Gaussian ones. And we believe that this will have an important implications in quantum communication. Now I will move to some of our recent work towards quantum computation. Now, one of the promising protocol to implement quantum computer is one-way quantum computer. The basic principle in this computation mechanism is the following. So you have an initial state. You evolve this initial state with a suitable Hamiltonian, and that will give rise to an evolved state. Now you manipulate evolved state to realize quantum gates, which are required to build a quantum computer. So from this, we understand that understanding evolution of quantum states are important. Specifically, understanding evolved states or the properties of the evolved states are important. Now, on the other hand, it has been shown recently that dynamical quantum state can mimic equilibrium physics. And this gives rise to a novel phenomenon called dynamical quantum phase transition. We have shown recently that the multipartite entanglement can detect such dynamical quantum phase transition. And we think that these results can be important to build a one-way quantum computer. So some of our work is recently published. Actually, the work in Physical Review Research is just published yesterday. So again, I saw that in Orijit's lab, it is possible to trap ions. So I want to stress the physical system in which we want to implement this one-way quantum computer can be realized in the laboratory by using trapped ions or cold atoms in optical lattices. So these trapped ion systems are possible physical systems to implement quantum many-body systems, and hence can be a possible medium to realize quantum technologies or to build quantum technologies. And also I have found that IIT Tirupati and IISER Tirupati both have a very strong condensed matter theory and experiment groups. So for example, I saw that the faculties work on quantum frustrated system, and there are quantum transport, etc. So in this respect, I wanted to tell you that we have shown in several of our recent works that if you consider quantum frustrated system or the resonating valence bond states, which are kind of important states in condensed matter physics, they poses high amount of entanglement. And this high entanglement content can be a resource for implementing many quantum technologies, including one-way quantum computer. So now I talk about, as I have shown, that quantum entanglement or quantum mechanics can help to build an efficient quantum computer. Now, in the era of miniaturization, even the thermal machines, it's important to build machines by using quantum mechanics. Now, in this respect, I only want to show one example, which is an energy storage device, that is battery. Now, every day we use battery, and we know the usefulness of battery from medical purpose to our daily needs. Now, usual battery stores electrochemical energy and converts it to electrical energy whenever we require. Now, recently we have shown that if you have an interacting spin-half model, that can act as a battery. And we can use, for example, quantum XY model which can be realized nowadays in ultra cold atoms or in ion trap, can act as a quantum battery. And when we can use local magnetic field to charge this battery. Now we show that if you have an interaction, so interaction strengths play a crucial role to increase the performance of the quantum battery, compared to the model where there is no interaction. That is the classical model. Now, moreover, we have shown that if you have disorder in interaction, that is any impurity in interaction, that also can enhance the power of the battery. Now, in experiment, impurity is inevitable. And so, our result has a direct implications when we want to build quantum battery in laboratories. Moreover, I mean, any process or any quantum technology that we want to build, that will suffer from decoherence. So there will be an environment which will actually decay some properties that we require to build quantum technologies. Now, this also we have addressed recently in the area of quantum battery, and we show that the situation is not that bad, because there can be a Markovian or non-Markovian noise that can help to store or extract energy from the battery. Now I come to the last part of my talk, where I will address certain fundamental question. So we call something called masking of quantum information. So what is masking? So if quantum information is hidden from subsystem and spread over quantum correlation, then we call it masking of quantum information. Now, if you replace this quantum by classical, that means if we talk about classical masking of classical information, so if classical information is hidden from subsystem and spread over quantum correlation, this is possible. So masking of classical information is possible. However, we show that masking of quantum information is not possible. So we arrive a theorem called no masking theorem. Now, no-go theorems has a very good, very important impact in quantum information processing task. For example, we know that there is a no-cloning theorem which tells us that copying of quantum states is not possible. Now, this no-cloning theorem is important to reach or to obtain the security in quantum cryptography. Now, we show that this no-masking theorem also has application in secret sharing protocol. Now, this secret sharing protocol is a quantum cryptography protocol involving several senders and receivers. So we show that the no-masking theorem, just like no-cloning theorem, no-masking theorem has application in quantum cryptography, which we can plan to implement in a quantum network. As well as there is something called no-qubit commitment, where also no-masking theorem can be applied. Now, this work was featured in physics 2 years back. Now, with this, I come to the end of my talk. So I somehow try to give a flavor of the directions which we are addressing at HRI. So this is the members of the QIC group at HRI. We currently have 15 PhD students, 5 postdocs, and 3 faculty members. And we also have a large number of visiting students who visit. As Dr. Miso was saying that as a theoretical physicist, our also aim is to train students to create manpower. So we also teach QIC 1 and QIC. So 2 courses, compulsory kind of optional courses in MSc program as well as PhD program. I hope that when the pandemic will be over, some of you are interested. So please visit us. And thank you very much for your attention. And again, I want to congratulate all of you for this center. Thank you.
Thank you very much, Aditi. Very fascinating talk, and your work on this no masking theorem is of great importance. Dhananjay Nandi has a question. Dhananjay? Dhananjay, can you come up?
I had questions to Lokesh da.
Oh, so I guess we will.
You can talk later.
I noticed it later. I'm sorry, Dhananjay, but maybe we can come back to this a little later. We are all in touch with each other anyway. Any other question on Aditi's talk on quantum technologies? It's very heartening to see that Aditi and Arijit are interacting in this area, and I'm sure that some good science will come out of it. Yes?
Yeah, so just I had one quick question regarding this dynamical quantum phase transition. So we are aware of quantum phase transition examples in condensed matter physics and in atomic molecular systems. So can we come up with an example of such a dynamical quantum phase transition in, let's say, in a condensed matter system or a AMO system, like a realistic example?
Yeah. Actually, that I haven't explained because of the time constraint. But exactly what you said, what I talk about this dynamical quantum phase transition is in quantum spin models. So suppose you know that if you have a XY spin model, then it undergoes a quantum phase transition from paramagnetic to ferromagnetic or antiferromagnetic phase. Now, if you the questions in dynamical phase transitions, because if you now start with one of the phase, so if you start evolution, so your initial state say is in a ferromagnetic phase, and then you quench the system in another phase, like the paramagnetic phase, then we can see that the system or the evolved state can show some non-analyticities with time, and that is called the dynamical phase transition. So this you start with a 0 temperature, for example, the evolution. Of course, during evolutions, you are not aware of the temperature. But if you do that, if you quench the system from one phase to another during dynamics, and you see that non-electricities with time, we call it to the dynamical quantum phase condition. So this is exactly what what people have introduced, and we show that in this respect, entanglement plays a crucial role because it can really detect this phase condition. And also in our recent work, we are able to show that if you have a thermal system, there also you can have a quantum critical region, which also can be detected by quantum entanglement.
Okay.
Thank you very much, Aditi, for your very fascinating talk. And we really look forward to an opportunity to have you with us in Tirupati and interact with our colleagues over here. So let me move on to the next talk, which is a very important one, because exploring fundamental laws of nature requires very sophisticated experiments, sometimes pushing and testing the quantum limits, and it requires light sources. So we will have Professor Ravindra Kumar, who will talk to us about the physics with extreme light. Ravi?
Yeah.
Yes.
Thank you. I will just start this. Yes.
Yes.
Okay. So it's visible now? Can you see?
Not yet.
Not yet.
Well, it takes. Is it okay now?
I am closest to you, but still I cannot see.
Yeah, that's very interesting. Let me see what has happened here. I said share the whole screen. So,
no, just a window. Share.
It should be a little more intense.
Okay. Yeah, I can understand that. So, 1 second. Let me just go here. So what am I supposed to do? I'm supposed to share the whole screen.
Window. There's a window option. Just that window.
Okay. Yes. Share. Okay. We've been using Zoom a lot, so this is new.
Yeah, coming.
Yeah, it's coming up.
Okay. So I'll just go to my talk now.
Yeah.
Yeah, it's good.
Okay. So now I'm visible.
Yes.
Okay.
Go ahead.
Great. Firstly, happy birthday to CAMOST, and it's suitably timed. I think it's just on the eve of the Independence Day, so I think it's a great occasion. It will be remembered forever because of its this unique day that we have chosen here. And Professor Deshmukh, congratulations! You have worked really hard, persistently for decades, and I think it's become a reality now. I also wonder that Tirupati is actually a pilgrim center, as we all know. So I'm hoping that there'll be pilgrims to your center from all over the country and all over the world, and hopefully all the things that you wanted to do, you get to realize in the decades to come. So the reason this presentation, of course, is for shedding some light on the possibilities that a new center might think of doing. And even if you do not actually build up everything in this direction, there are things that are possible with collaborating with TIFR and other centers around the world. So maybe this will open directions that you have thought of, but may not want to do because the emphasis is on something else. So with a little bit of effort, I'm sure you can actually even enter this area. So this is about extreme light, and so extreme light is actually powerful bursts of laser light, as they have, and the reason for extreme will become obvious very, very soon. So these extreme lights are extreme in terms of the durations are extremely short, typically femtoseconds, and the intensities, because of the power that goes up because of the low duration, the small duration of the light, and for any energy that you can muster from the laser pulse, so the power just shoots up. The shorter the time duration, the higher the peak power. And if you boost the pulse energy to any extent, you keep on, either you increase the pulse energy or you shrink the pulse duration, and you can maintain the same power, and you can do some very interesting things. So the extreme is also because of the fact that it catches most atoms and molecules, or even the motions inside a solid. It really freezes the motion, meaning it is faster than the time scales that are used for typical motions inside atoms and inside molecules, certainly. And soon, I think we'll be able to do even faster than the processes inside atoms. So because of the fact that you can freeze it, you can actually see, you can catch systems totally off guard, and you can dump in huge amounts of energy into one part of the system while the other part of the system remains as if it's been untouched by the excitation. And so for a pulse like 100 terawatt power that you can produce in 30 femtoseconds, you focus it to an area of something like 10 microns or so, then you will have intensity which is 10 to the 19 watts per centimeter square. What does this mean will become obvious shortly. But again, I am reporting from the shores of the Arabian Sea like Lokesh, and there's a different picture. Please visit whenever you can and see our labs and see what we are doing, both in the high energy, the charged ion lab, and also the laser lab. And the lasers, the team that does most of the work, they're all here, young people, lots of young people. And I'm sure some of you from the CAMOST or from both the IIT and ICES can also participate with us in some of these experiments. You're welcome. And hopefully we can do something newer and better. So this is the laser that we have at TIFR. We have two such laser systems with high peak power. This is one of them. And this one produces peak power of 150 terawatts at 5 hertz. So these are complicated laser systems with several subsystems involved, but still not as complicated as the traditional high power systems that have been in existence for decades now. And the reason that these lasers have shrunk in size is because of the short duration that they use for producing this peak power. And the revolution in this obtaining this peak power was triggered by this Donna Strickland and Gerard Moreau. Donna was actually a PhD student of Gerard Moreau at Rochester when they struck up this idea, implemented from radar technology, adapted to the laser technology, and then unleashed a revolution in high power lasers. And Gerard Moreau, on a visit to TIFR in 2010, standing there with us, with me and colleagues. So to my right is M. Krishnamurthy, who has also been a major, driver of this work at TIFR, and then our students and colleagues. And so Gerard Moreau continues to work very actively. He's relentlessly pushing the field towards higher and higher peak intensities. So this sets a scale for what it means to have an intense light field. So if you compare with the electric field of a hydrogen atom, the 1s electron experiences 10 to the 9 volts per centimeter, and that converted to intensity becomes 10 to the 16 watts per centimeter square. But today in the lab, in a couple of labs probably, we can produce intensities which are 10 to the 22 watts per centimeter square. At TIFR, we can produce 10 to the 20. So we have beaten the Coulomb intensity by orders of magnitude, something like 1,000, 10,000, or even 1,000,000 times larger intensities we can produce. And so the Coulomb field has been exceeded by a factor of 1,000. So that's remarkable. It's never happened in the in the history of experimental science that we can overwhelm the fields inside matter with such monstrous in such a dramatic fashion. So this is an example of what happens when light interacts with, for example, it's not a single atom or a molecule, but a solid where there are lots of atoms are there, and with the electronic clouds. So suppose you bring in a laser pulse and it ionizes, invariably it ionizes all the atoms in the focal volume. It heats them up, and it also heats some of them to extraordinarily large velocities, extraordinarily large energies. So typically the plasma temperatures, the bulk plasma temperatures that you can produce will be of the order of 10 to 100 eV or hundreds of eV, depending on the intensity. And some of these electrons which have been ionized can be given energies as large as billions of electron volts. So the light photon of 1 eV now starts producing particles which are millions of electron volts. And this quite in contrast to what you can do with accelerators, where you come with a very highly high energy particle, and then you transfer certain energy, which is a small fraction of the particle energy itself. Here, the particle energy is very small, but you can couple huge amounts of energy to the excited system, the particles in the excited system. And so this is one snapshot that hopefully you'll carry with you, that if you have a high intensity laser above 10 to the 18 watts per centimeter square, and you impinge it on a system, it could be a gaseous cluster, it could be a solid, it could be a droplet, anything that you can think of, then you do almost all sorts of physics. Firstly, you have a very high state of excitation. Obviously, plasma is formed, but the plasma is not the normal plasma that you encounter when you're doing solid state processing for making films and so on and so forth in a condensed matter lab. But this is extremely high energy, high energy density plasma. So it has high density of particles. It also has high temperatures. And in this little piece of matter that's been excited, you can have atomic physics of exotic atomic physics happening. You can have solid state physics, which is happening, which is unheard of in the normal circumstances. You can, of course, have plasma physics. You can have particle acceleration happening to millions of electron volts. So you can think of, how particles are getting such large excitation here. And the particles actually stream into the solid, lots of them at high densities, at relativistic velocities. So you have currents which are giant in nature. You can have mega ampere current pulses. You can have current densities which are trillions of amperes per centimeter square. So they can produce extraordinarily large magnetic fields. And this excitation can now produce high energy protons from the rear surface or the front surface, from the molecules which are absorbed there. It can also produce fusion reactions. And the fusion reactions can then give you neutrons if you have appropriate materials. For example, if you have a deuterium there, then you can produce fusion from the deuterium ions there, deuterium nuclei. And then you can, the gamma rays that are produced by Bremsstrahlung from here can then break up into electron-positron pairs. So you can have a positron production from there. And X-rays, gamma rays are obvious from the Bremsstrahlung and from several coherent emissions that happen from here. And of late, this is also a sort of source of what is becoming very popular, is the terahertz radiation. So this has become a very hot, energetic source of terahertz radiation. And so all sorts of physics is happening here, and you can choose what you want to do and then do that physics. So it's a sort of one-stop source for physics, from astrophysics to atomic physics. And so the way to see this is actually extreme states which couple high density because of the short pulse excitation, ultra short pulse excitation, coupled with high temperature. So the electrons are kicked up to very, very high energies, but the density doesn't change because the kicking is happening on a time scale which is much faster than the ionic response time scales. So this has become known as what is called the HEDS, or the high energy density science. It creates extreme states. And if you look at this picture here, so you have log of the temperature plotted on the y-axis, log of the density plotted on the x-axis, and you can see lots and lots of physical systems in the universe all sharing the same 2D surface, 2D plane. So the central portion is what people are trying to explore at the moment with the present capabilities, but they're trying to expand the portion that is being explored with newer devices, newer technologies, and newer kinds of excitation. So this is again another thing that you can see, that you have plasmas of all types, from ultra cold neutral plasma, probably useful for quantum computing, all the way to inertial confinement fusion, which can produce energy for driving most of our labs and most of our daily life. So inertial confinement fusion there's been a huge effort, and the densities there are monstrous. For example, you can see I have plotted this 10 to the 8 kelvins at something like 10 to the 27 particles per cc, meter cube. So the laser fusion effort has been going on for a long time. Hopefully it will succeed in the near future, and then we'll have all the power that we need, which is safe and sort of non-polluting. So the TFR group has pushed lots of these things. I will not get into any of the details except one or two. And I just want to show you that the rich physics that you can do with a tabletop laser like this, it's just really fantastic. You can look at giant magnetic fields which are produced, as I told you, only in this context on the Earth. and you can do relativistic electron propagation inside matter, and you can look at enhancing these emissions using tailored targets, and you can also do you can make an accelerator from here to produce particles for secondary excitation of atoms and molecules, and of course novel terahertz sources. So this is one example that I want to show. This been work done totally at TIFR, and you can see M. Krishnamurthy was the guy who led this work, and E. Krishna Kumar, who's in the audience there, has contributed to realizing this accelerator. So it's a compact laser-driven plasma accelerator for neutral atom beams. The world has been looking at accelerating charged particles, both negative and positive charged particles, for a long time. And that's obvious because you put the particle in an electric field and you can accelerate it to whatever energy you want. But how do you excite a neutral atom? And how do you produce MEV neutral beams? There's not been any effort. In fact, I dare say that perhaps this is the best way of producing a neutral atom beam at MEV particle energies. So if you want to read the details, please do read this paper that appeared in 2013. But I just want to say that since then, it's been expanded to produce neutral negative ions at high energies. And so it's become a one-stop source for positive particles, neutral particles, and also negative ion beams. So this is yet another example is to look at magnetic fields. I told you that magnetic fields of extraordinarily large magnitude can be produced here on the Earth. And so this is something like a 65, 70 megagauss magnetic field that we saw in the lab. And so what do you have? We also explored its spatial and time evolution of this giant magnetic field in the plasma. And these are the snapshot pictures of the 2D evolution of that, covered over something like 7 picoseconds after the excitation by the laser. And it turns out that these patterns can be analyzed to look at what is called the turbulence that can be created inside this plasma, which actually is reflected in this curve, in this graph here, that you plot the log of the magnetic energy versus the inverse of the length scale, then all the patterns, though they look wildly different in their spatial manifestation, in the power spectrum, they all look very, very similar with a slope that is close to -2. And this indicates, the power law indicates actually that the system has become turbulent. And this, by the way, is an example of astrophysical turbulence. So the systems in, the plasma inside the sun, inside stars, inside the Earth, around the Earth, in the magnetosheath, in the solar wind, in various places, is actually the magnetic field becomes turbulent. And till now, there have been no earthly parallels of that. But this laser plasma can actually show you that you can mimic that turbulence. So the moment you can mimic the turbulence on a tabletop, you can probably push the astrophysical models. You can give them some crucial information that tells you what may be or may not be happening and how to tweak these models further. So of late, I wanted to give you this another example is that of a broadband terahertz radiation source. This is not at the 10 to the 19, 10 to the 20 watts per centimeter square. This should be implementable with a little bit of funding, even at CAMOST. And I don't know what all it can do. I think it can unleash a whole range of activities in this area using terahertz radiation. So this is at 10 to the 14 watts per centimeter square from a femtosecond laser. And this is simple liquids like acetone and methanol can be excited. The laser forms a plasma filament, and the plasma then starts radiating copiously, at very high energies. In fact, this is a tabletop source that produces something like 50 microjoules of energy, terahertz energy over a range of 0 to some 60, 70 terahertz. And if you look at the competing sources in the lab, which use semiconductor antennas, they are a fraction of a million lower than that, than this in energy. So this is a very nice example of what can happen. And with just a little bit of modification in the kind of systems that you study. Nobody had looked at liquids because they thought liquids absorb terahertz, so there's no point in looking at them. But liquids do absorb terahertz, but they still leave a lot of terahertz for you to extract. That's been the bottom line here. So for more of our work, please do visit us in the lab to discuss with us, of course. But if you can't, pandemic or otherwise, then please look at this web page where you can download most of our work, the papers and the thesis and so on, and do send us questions. and tell us how we can collaborate further on this in these areas. The future is very exciting for the field. People are pushing these intensities to, at the moment I said this 10 to the 22, they want to go to 10 to the 24 in the next few years, and major facilities are being built around the world. We should certainly collaborate with them, and CAMOST should join these efforts in the short run, also in the long run. So these are the big pillars of the extreme light infrastructure being built in Europe, and we should all join and do experiments at these centers, because it's becoming highly collaborative. As Dr. Mitra was saying, this should be highly collaborative work which pulls all our resources, IITs, ICERs, TIFR, everyone together going to do experiments at this. And very soon the dream is to reach something like 10 to the 29, 10 to the 30 watts per centimeter square in the next few decades. Perhaps the youngsters in the audience would be alive to see that this thing, and maybe use this in, whenever these things happen. So we're going to enter the quantum electrodynamics era. So then we can do fantastic things with these kind of lasers. So what is in it for CAMOST? I thought I'll just put down some few ideas. So basic physics that's immediately available is looking at highly charged ions, and of course atoms in ultra strong magnetic fields, which is a fascinating topic. You can produce things like one-dimensional atoms in an ultra strong magnetic field. You can look at extraordinarily large Zeeman splittings, and I don't know what all it might unleash for our understanding of atoms. And the secondary sources that I hinted, beams of relativistic electrons, fast ions, X-rays, can be used for basic studies. They can also be used for imaging, ultra-fast dynamic studies, material modification, what have you. Then time domain. I see that there's interest in attosecond physics at the CAMOST Center. Then imagine you could probably think of experiments which are done right in India with attosecond pulses of coherent X-rays. So these are attosecond pulses. They are also coherent because they're being generated by the laser using either a solid target or a gaseous target. And if you push the limits, you can actually go to quantum electrodynamics at 10 to the highest intensities, look at processes like radiation reaction, and all that can be done on a tabletop in a small, qualify the small by saying that it may not be small in our normal thinking, but small compared to what the big facilities so far have been putting out. And of course, the theoretical and the numerical avenues are, they're just enormous. So this is one example just to show that what we've been doing in our own labs here, using electrons and X-rays. So this is an image that's been produced by M. Krishnamurthy, MK for short, as is known in the community, and colleagues. So this is imaging of, you can see the bones, joints, everything being imaged with a source that's been set up in our labs at Hyderabad. As you know, TIFR has a new campus at Hyderabad where we now want to expand. And so this has been one of the very preliminary experiments with very, very highly impressive results. So at Hyderabad, we want to now do big things, which we can't do in Colaba because of lack of space here. And we want to look, we are in the process of setting up a petawatt laser, which should give us something like 10 to the 20, and with good conditions, 10 to the 21 watts per centimeter square, perhaps. And with that, we should be able to do astrophysics. We should be able to drive particles to extremely large velocities. And we should be able to do warm condensed matter where there's a huge amount of effort to be explored. We don't understand warm condensed matter because the ion correlations and the ion potentials become extremely important. It's not a plasma state at all. So it's a system that we don't have any models for yet, reliable models. And we also want to get into futuristic particle physics areas. So this is one place, and Hyderabad is not too far from Tirupati, right? So it should promote lots and lots of near neighbor interaction. And hopefully there'll be lots of exchanges between the places. And in fact, I think the CAMOST idea is a terrific idea because it's for the first time that the atomic, molecular, optical sciences they've been thought about for a long time as one unit that can bring lots of benefits if people put their heads together. Finally, it's happened, and I think we should all exploit this. We should thank Professor Deshmukh for all his efforts over the years and everybody that has contributed to making these things happen. And I was just about to say Professor Ganesh has been known to remove hurdles in more ways than one. And as Lokesh said, when Ganesh and Satyanarayana meet, I guess the possibilities are limitless. Thank you very much for your attention to this talk.
Thank you very much, Ravindra Kumar. Very fascinating talk, and for pointing out the very exciting opportunities which are coming up, which I'm sure the young scientists in the audience will take a full advantage of. Is there a question from anyone?
Sir, may I ask? Hello,
yes,
sir.
Yes, please.
Yeah, so this is Ritesh from IIT Tirupati. Sir, if you could briefly tell us the influence of this pulse duration on plasma properties, like especially the temporal and spatial. Like if there are studies happen in this direction,
Okay,
or the field
I
is
would
still
say,
ongoing.
I wish I had more time, so maybe I should visit Tirupati and talk to you in person about all this. And we have done a lot of work. In fact, much of our work has been on the dynamics. You know, when you excite with a femtosecond pulse, everything happens on very, very rapid time scales, right? You're just kicking up. In fact, you're going 0 to 10 to the 19 watts per centimeter square in just a fraction of a picosecond. And that's truly astounding. Nobody has done that before. But so it goes through several states of evolution. And we have captured, even in the plasma state, if you look up our papers on our website, you will see that we've been obsessed with looking at things as they happen, where they happen. So as they happen is on ultra-fast time scales, and where they happen is which part of the plasma is actually bubbling out, which part of plasma the magnetic field is behaving in a certain way, and so on. So that's been our USP. And I would urge you to maybe just look at those papers, and then we can have probably a meaningful discussion. So there's been lots of work, not just other labs too in the world, but it turns out that the big labs have been focusing on the big questions, so leaving many small interesting questions for us. So it's one thing where even CAMOST can probably make a very important contribution. So the ultrafast dynamics is certainly very, very important.
Thank you so much, sir. I'll surely look at it.
Please look up, yeah. Thank you.
We have had excellent talks by Lokesh, Aditi, and Ravindra Kumar, and we are slightly behind the schedule, but what is important is is to recognize that the primary inspiration for CAMOST comes from the young scientists at IIT Tirupati and ISER Tirupati. So I would like to request the program coordinators at these two institutions, Arijit Sharma and Sunil, to speak to us. Arijit first, so that they will express their aspirations to us. Arijit?
Yeah, thank you, sir, for giving us this opportunity to speak on this occasion. My heartfelt thanks to all the distinguished scientists who have taken part in this meeting, especially the scientific committee members, as well as the two directors and the distinguished speakers. As Dr. Arbinda Mitra has said, that collaborative activities, and also that has been emphasized by Professor Ravindra Kumar, that collaborative activities is a key to encountering the challenges of the physics of the 21st century. So keeping that spirit in mind, we have, as two young institutions at IIT and ISER Tirupati, come forward, and we have leveraged this together to start the Center for Atomic, Molecular, Optical Sciences and Technologies. So with this center coming in shape, we now both have tremendous opportunities as well as responsibilities. Opportunities in the sense of what has been projected by Dr. Mitra in terms of the various national missions, where we can contribute in terms of both human resource development and technology development, and responsibilities in the sense that with all these missions, there is a growing need for the country to develop business intellectuals and develop technology that can be implemented for the benefit of society. So both of that is there. We are fortuitous to have ISER Tirupati as an institute very close to us, because ISER Tirupati is mostly focusing on fundamental science aspects, and their programs in AMO science and technology are looking at atmospheric sciences and physics, and atmospheric chemistry, then single molecule batteries, and biomedical applications using optical tweezers. Whereas on the other side, in the IIT side, we have a complementary expertise. So Myself, I am working on quantum communication experimental program, and then working on the development of sensors, atomic sensors, and frequency metrology. My colleague, Dr. Vinay, he is working on theoretical ultrafast dynamics and attosecond dynamics. Then my colleague, Dr. Ritesh, he works on experimental and theoretical plasma processing technology with applications to water purification, agriculture, food processing. And then finally, of course, we have our mentor, Professor Deshmukh, who has been doggedly pursuing this idea for quite some time. And finally, this has been realized by him. So we are very fortunate to have him on our side. So this is all what I had to say. And we look forward to your support and encouragement so that we can fulfill all the aspirations of both the society and the country at large. Thank you.
Thank you, Arijit. Sunil?
Yeah, thank you, sir, for giving me an opportunity to talk in this CAMOST inauguration function. I would like to thank all the distinguished scientists and other people who joined joined in this meeting. Being a part of the CAMOST team, today is indeed a special day in my own research career. I believe that it is all my colleagues associated with the CAMOST feel the same. It is not a common for an early career researcher to be an integral part of establishing an emerging center of national and international importance. In fact, most of us associated with CAMOST are in our early faculty careers, which indeed something special for the center, and I see it as a virtue. One reason why I believe so is that we do not have to be biased by too much of our experiences. Each of us have our own strengths and weaknesses, and we can easily adjust with that while working together. Our greatest limitation would be our inexperience. However, from what we have learned from working towards establishing the center so far, I can certainly say that this is not going to be an issue at all because of the tremendous support from Professor Deshmukh, who is the mentor and convener of CAMOST and the directors of the two institutes. In fact, I would like to address Professor Deshmukh as the founder of the center, which in no way is an exaggeration. In addition to very inspiring support from the Professor Deshmukh and the directors of both the institutes, we receive guidance from the heads of the departments of the physics at ISA Tirupati and IIT Tirupati and all the members of the Scientific Advisory Council. In CAMOST, we have a very highly motivated and talented group of faculty working in several frontier areas of atomic, molecular, and optical sciences and technology. Being a part of the CAMOST, our ambitious projects would not have to be restricted by limited availability of resources, which typically happens when one works as an individual. In CAMOST, we will be working closely together on collaborative projects which are already in place, especially because the CAMOST is already there, and new collaborations with other scientists throughout India and abroad are also being established. The greatest strength of CAMOST, in my opinion, is bringing together the science and technology into a single platform by extracting resources from both the institutes, ISA Tirupati and IIT Tirupati, as well as other institutes of our adjunct members, and also many other institutes later on. Given all this, we believe that we will be able to make CAMOST to have a very bright future in the scientific and technology map of India, not just in AMO science and technology. So now I would like to make a personal remark because I mean the center is actually the result of incredible determination of Professor Deshmukh, and I was actually doing my PhD under his guidance a decade ago, and now even before that he has started to establish such a center, and now I am personally privileged to be an integral part of the team. This in turn benefits a lot of young researchers from ISA Tirupati, IIT Tirupati, and many other institutes who start off their early careers with so much of support from the community. I do not have any doubt that establishing CAMOST is going to be a huge boost for our scientific research and technology developments in India. Thank you.
Thank you both, Arijit and Sunil. As it was mentioned earlier, CAMOST aspires to be a national resource, and even here at Tirupati means it benefits not only from the AMO scientists, but we have a very good group in condensed matter physics, and there are other experts in other centers. Some of them even participated in our meeting last year when which really nucleated the formation of CAMOST. So there are a number of adjunct members of CAMOST from various other institutions. I will request some of them to share their remarks. So Dr. Kaushik Saha from IIT Dharwad first. Kaushik.
Thank you, Professor Deshmukh, and very good evening to all. It is indeed very heartening to see that CAMOST has taken shape. Such a center is the need of the hour for the AMO physics community to be able to address frontier problems in AMO physics. If we look globally, scientists and researchers are coming together to be able to address new problems and challenges of 21st century. CAMOST, I feel, will give us this platform where collaboration will drive the AMO physics research in India. For a faculty like myself, coming from a young institute, it presents a unique opportunity to do collaborative research and to be able to pool our resources and expertise, which in turn would enable us to address bigger problems and also create impactful research. I look forward to work with my colleagues at IIT Tirupati and IISER Tirupati, and also my colleagues from other places under the aegis of this center. Before I end, I wish to congratulate Professor Deshmukh and the entire team at IIT and IISER Tirupati for their efforts in bringing up this center. Thank you.
Thank you, Kaushik. Amongst the several institutions which have already established a connection with CAMOST at Tirupati, we also have IIT Patna, and Dr. Jobin Jose will talk to us from IIT Patna. Jobin?
Thank you. Am I audible, sir?
Yes, go ahead,
Okay.
Jobin.
Yeah, dignitaries on the virtual stage, Chief Guest of the event, Dr. Arabinda Mitra, Scientific Secretary, Office of the Principal Scientific Advisor, Professor K.N. Satyanarayana, Director of IIT Tirupati, Professor K.N. Ganesh, Director IISER Tirupati, Professor P.C. Deshmukh, Mentor and Convener of CAMOST, and distinguished speakers of the event, and all others who are assembled in the virtual platform. First of all, greetings from IIT Patna. It's an exciting moment for all of us since the Center of Atomic and Molecular Optical Science and Technologies is officially inaugurated. I'm extremely delighted, of course, to be part of the same. As we are knowing, members of the CAMOST are leaders or part of research groups working in the frontier theoretical and experimental AMO physics and technologies. That is why multiple thrust areas to cover the frontier fields of AMO science have already been identified. One of the major objectives, as I was going through the flyer of the CAMOST, that it is to facilitate exchange of information through collaborative research activities. Certainly, we do collaborate, but under the umbrella of the CAMOST, our collaborations will get more exposure, and the collaborative research will gain extra momentum. I'm sure about it. To further fulfill this objective, symposia, conferences, public talks, etc. can be arranged, and I'm sure these are few among the action plans of the center. I look forward to contribute in the discussions and collaborations in the center, and I wish best wishes to all the interviewers of CAMOST. Lastly, I should thank the organizers and coordinators of the center, especially Professor P.C. Deshmukh, who pursued this challenge, who visualized the center and executed implanting. Thank you so much.
Thank you very much, Jobin. The Physical Research Laboratory at Ahmedabad has played a very important role in developing atomic, molecular, and optical sciences, and they have scientists at this laboratory have made a huge contribution to AMO science in India. We have with us Dr. Rajesh Kushawaha from Physical Research Laboratory, and I invite Rajesh to share his remarks with us. Rajesh?
Yeah. Professor Deshmukh, Professor Satyanarayana, Professor Ganesh, and Professor Mitra, I salute you and salute for your visionary leadership that you have made this platform, which is not less than a breakthrough for a young researcher who are joined in many IIT, university, and other national institutes. Young researchers and scientists join there, they are seeking a kind of facility or research opportunity, and it's very challenging in the beginning to have to start some research lab. Such a kind of center has been, I mean, to study such center is already in discussion since almost 1 decade. In every conferences, in the plenary discussion, there was a discussion on the need of the center based on the, I mean, the requirements for the upcoming technology. For example, already Professor Ravindra Kumar mentioned that auto-second science, Terahertz and other, even the national mission on the quantum technology that is coming up. So to grab that, to understand and develop the technology, we should have a foundation. And this discussion was going on since many years, but it was not possible to realize, although the effort of Professor Deshmukh was huge. I mean, he was trying and he has attempted many times. I thank to Professor Narayana again and Ganeshan and Deshmukh that they have actually come together. See, this is a kind of a facility that giving to an opportunity to all of us to work on the frontier topic of atomic and molecular physics and develop a technology. So with this, I will thank again.
Thank you very much, Rajesh. As was mentioned earlier, we have a very distinguished senior scientist to guide us, and some of them are able to participate in the meeting today. I will request first Professor John Costello from the Dublin City University to share remarks with us. John?
Thank you, Pranav. Greetings to everybody from Ireland. It's been a real pleasure to see the inauguration of CAMOST, as you call it, today. I've known Pranav for well over 20 years now, and I've also known he's had a vision for having a major center on atomic, molecular, and optical sciences and technologies in India, and it's a great day, and congratulations, Pranav. Requires not just your vision, but it also required the leadership from both directors to get behind you and drive this and make Tripati really a center for not just the fundamentals, but I also like is this idea of translational research, where you will, you know, make sure that you have the best work that you can do in the fundamentals, but actually translate it. And that's where the funding is going to come from, as we heard from Dr. Mitra. I will do my best to support you, Pranav. It's been a while since I was in, the last time I met you, you were in IIT Madras, so it's been a few years since we met at Madras. I see Professor Vijayan is also there from IIT Madras. So I will do my best to support. I've been very, very impressed with the enthusiasm, the quality, all of the things that you need to put in place to make a center successful. Mostly your leadership. And I think that's what everybody will depend on over the next few years. So many thanks. I will help personally, but I will also try to use my own network and leverage it as well. I see many areas of interest. I was very interested in TIFR, Professor Ravindra Kumar's talk on terahertz generation. I'd have lots of questions for him on that. But so this collaboration, which goes right across India, pan-Indian, as is mentioned in your text, I think is going to be very important. So I'll finish up by saying I will give 100% support. I think it's a fantastic initiative. I'm glad to see it come to fruition finally, and I wish it every success in the future, and I will do my best to help it achieve that success.
John, thank you very much. CAMOST certainly needs guidance and support from all of you, and we are very fortunate to have very distinguished scientists. John himself has led very large research groups in Europe, so I think your experience is going to be extremely valuable to the center. Professor Kumar has made a huge contribution to the experimental program in AMO Sciences in India. He has been he was also present at the meeting that was mentioned earlier on 20th March and gave his recommendations. So I request Professor Krishna Kumar to share his remarks. EK?
Yep. Good evening, everyone. I'm very happy to be present at the inauguration of CAMOST. I congratulate the directors of IIT Tirupati and IISER Tirupati, Professor Satyanarayana and Professor Ganesh for creating this center. I also congratulate Pranava Deshmukh for his initiative and the young colleagues from the two institutions in putting forward the proposal.
EK, could you come closer to the mic?
Yeah. Do we need to repeat?
No, go ahead, but closer, yeah.
After attending the initial meeting on the proposal, I had given my views on the need to have a large-scale activity in the area of AMO sciences in the country. I reiterate again on the fact that AMO science is the fountain of our modern technologies and the mother of all physical sciences. Unfortunately, the science leadership in the country did not have a broader vision to support this area of activity as was necessary. I sincerely hope that the setting up of this center is a very good beginning to correct the lopsided vision that existed. I wish that this center grows in excellence and there will be many such centers set up in the country in the near future. Thank you.
Thank you very much, EK. We have Professor Bhanu Pratap Das, and I request Bhanu to share his remarks. Bhanu is now in Japan, and it is pretty late in the evening there, but thanks for staying with us, Bhanu.
Okay, so thank you very much. So can you hear me?
Yes, Bhanu.
Okay. So let me begin by congratulating Professor Deshmukh and the directors of IIT Tirupati and IISER Tirupati for bringing CAMOST to life. I mean, they really made it a reality, and many, many congratulations for that. I'm very impressed by the wide range of programs that you plan to pursue at CAMOST. And I'll just say a few words about quantum technologies, which is my main focus at the moment. I'm currently working mainly on quantum computing. So a lot of what I wanted to say has already been said by Dr. Mitra and Professor Aditi Des Sen has given you a flavor of the field. There's just a few things that I want to emphasize. I mean, one thing is that AMO sciences has really been very crucial for the development of quantum computation. In particular, the first prototype quantum computer that was built in the lab was an trapped ion quantum computer, for which David Wineland got part of his Nobel Prize. Now, since then, the progress using atomic and molecular systems has been absolutely remarkable. And one of the most promising platforms for quantum computing today involves cold atoms, Rydberg atom arrays, and possibly polar molecules. So there's a lot to do in this field in the actual building of quantum computers. What I think is less well known is the fact that atomic and molecular theory have a very, very important role in this. Once you build a quantum computer, what are you going to do with it? You actually want to do computations. You actually want to do calculations. Now, atomic and molecular calculations are now primarily done using classical computers. But it has become fairly evident in the past 2 or 3 years that quantum computers are better suited for atomic and molecular calculations in the long run. And to that end, efforts are going on in various places, particularly in IBM, Google. And that's a field that I'm currently involved in my group at the Tokyo Institute of Technology is collaborating with groups in Osaka City University and an experimental group in University of Tokyo. And we've been able to do real, computations, that is atomic calculations on a quantum computer using 4 qubits. And this is using the quantum computer that was developed by Professor Nakamura, a pioneer in the field of superconducting quantum computers. And it looks possible that we can do calculations using a 20-qubit real quantum computer in the next few years. So who knows? I mean, it might be possible to achieve quantum supremacy through AMO systems. And I do feel that CAMOST would really engage itself in different aspects of quantum technologies, quantum information, communication, and in particular, quantum computing, I think, could be a very fruitful area because there are people in India who have plenty of experience in both atomic and molecular many-body theory. So with these few words, I'll end, and I'm congratulate again Professor Deshmukh and his colleagues and the directors of IIT and ICIT Tirupati, and my very best wishes to all of you in the future. Thank you.
Thank you very much, Bhanu. This meeting time has taken over your dinner time, and likewise the lunch time for Professor Roland Wester, who is with the universities of Heidelberg as well as the Innsbruck Research Center. And there are a good number of experimental physicists in India who have worked with Professor Wester. May I request Professor Wester to share your remarks? Professor Wester?
Yes, thank you very much, Professor Deshmukh, and warm greetings to all the members of COST and all of you, your distinguished colleagues in India and all over. It's my pleasure, and it has been really my pleasure to be part of this inauguration and to see all these activities that have been established, and seeing that atomic, molecular, and optical physics is so deeply rooted in fundamental physics, but at the same time so important for many applications in both in the basic sciences. Topics close to my heart are, for example, astrochemistry and the astrophysics of the interstellar medium, but also so important for many technical applications. We've seen laser applications before in the talks, and there are numerous others in quantum physics, for example, as was mentioned just before. From that point of view, it's so important to create collaborations within the AMO topics and also from AMO physics to other disciplines in nearby areas. That such an initiative as CAMOST is coming to be is really important to develop AMO physics further and to apply it to many other areas of science. And so in this respect, I very much congratulate you to having established this and for the foundation of CAMOST. And I very much look forward to seeing CAMOST flourish in the coming years and to many successes that will come out of it. And I also look forward to interacting with you more and more over the next years. And also maybe to come back to India at some point and visit. And in this respect, once again, congratulations and thanks for bringing us together here for this inauguration in this difficult and unusual times at the moment. I think it has been a great success already, and I really very much look forward to how it will develop in the future. Thank you very much.
Thank you very much, Professor Wester. I'm sure there is a very large community in India which looks forward to your visit to India. We also have with us Professor Steve Manson. He has been a huge support to the theoretical atomic physics program in India. A large number of scientists have benefited from collaborating with him. He has visited Tirupati a number of times and also visited both the institutions, IIT as well as ISER in Tirupati. He was also present at the meeting that was mentioned last year, which was a very important meeting which led to the formation of CAMOST, and he spearheaded the discussions at that meeting. So may I request Professor Manson to speak to us. Professor Manson, I noticed that he had logged in. Steve? I did notice a few moments ago that he was logged in into the meeting. Professor Manson? It seems that he may be having some connection problem. I definitely noticed that he was logged in. I saw his name come up. Oh, there he is. Professor Manson? Steve? Professor Manson, can you hear me? Steve? Hello? It is also very early morning in Atlanta from where Professor Manson is joining. Steve, are you on? I saw his name just a few moments ago again.
Yeah, it's there, Pranav. It looks as if his microphone icon disappeared.
Okay. Steve, is your microphone unmuted?
Well, if it's disappeared, it means there's some problem with the mic.
Oh.
So let's move on. You can come back as soon as he is able to.
Yeah, we are actually toward the end of the program, and you know, we have. So if I'll wait for a moment or two, maybe half a minute, and see if Professor Manson can join us.
Maybe you can announce for a dinner now, then everybody.
Yes. All right. So let me mention that all the other colleagues at IIT and ICER have contributed in a big way, directly or indirectly, and they include other physicists, chemists, and other colleagues in both the institutions, and also in particular the head of the Department of Physics at IIT Tirupati, Dr. Koteshwar Rao, and the department chair, Professor Ambika at ICER. Professor Manson is there. He's sending a message
my
there.
mic is on, but I don't know what the problem is. So he's having some trouble.
Yeah, so I think we will listen to Professor Manson when he comes next to Tirupati, and I hope it will be soon enough. And yes, thank you very much, Steve. I see your message. You have been here all through the meeting, so it's always wonderful to have you. There seems to be some problem with your microphone, and we miss your remarks here, but I know it will be made up for, because we certainly look forward to your visit. In fact, it would have already happened in March, and we were to have a meeting when Professor Manson was to be with us in the middle of March. It was scheduled between 15th and 25th of March at IIT Mandi. And that is when the pandemic was growing, and we canceled that meeting. Otherwise, we would have been stuck in Mandi, or many of us. So, Steve, we will listen to your talk at the earliest opportunity. I want to especially thank Dr. Koteshwar Rao and Professor Ambika as representatives of the entire faculty members at both the institutions, who have helped us in very many ways. And I request Professor Ambika to speak to us on behalf of all of them and propose a vote of thanks. Professor Ambika.
Okay, good evening to all of you. Directors of the Twin Institutes, Professor Ganesh and Professor Satyanarayana, Professor Deshmukh, Professor Safwan, expert members of the Scientific Advisory Council, adjunct members, principal investigators of the center, faculty colleagues, scientists, and students. It's my pleasant duty today to propose the vote of thanks in this very elegant e-session, the inauguration of the Center for Atomic, Molecular, and Optical Sciences and Technologies, CAMOST. It's a joint initiative of IISER Tirupati and IIT Tirupati. Dr. Arabinda Mitra, Scientific Secretary in the Office of the Principal Scientific Advisor, Government of India, was with us today as our chief guest. As part of the inaugural ceremony, he has e-released the center brochure and the video. He had to leave a little early due to some prior commitments. On behalf of all of us joining on this e-session, I extend our thanks and appreciation to him for sparing his time with us today and honoring us by inaugurating the center. At the very outset, I would like to thank the directors of both participating institutes, Professor Ganesh and Professor Satyanarayana. Without their guidance, support, CAMOST would not have been established. At every stage in its development and discussions, they have provided encouragement and appropriate mentoring. On behalf of all of us here, many, many thanks to both of you. The mentor and convener of the center is Professor Pranav Deshmukh, a well-established scientist in the area of atomic and molecular physics. He has been working on the idea of the center from the very beginning, very enthusiastic in taking it through the various required stages, untiringly letting it get across all the hurdles on the way to reach this day, to make this center a reality. Congrats to you, sir. And I am sure under your leadership, the center will go a long way and reach its goals. We all thank you with a big round of applause for your initiative and enthusiasm. We have brief but informative talks from 4 guest speakers today. Professor C.P. Safwan from IUSC New Delhi, who briefed us on the origin of the center. Professor Lokesh Trivedi from TFR, Professor Aditi Sende from HRI, and Professor Ravindra Kumar from TFR. They gave very interesting talks on the thrust areas in this field. On behalf of all of us, I thank you all for being with us today and for the very interesting talks. The Scientific Advisory Council of the Center constitutes 10 experts. I thank all of them for giving proper directions and guidance in establishing this center. Among them, the following members: Professor John Costello, Professor Krishna Kumar, Professor Bhanu Prasad Das, Professor Wester, and Professor Manson were with us. And special thanks to them for their very helpful remarks on this occasion. And also thanks once again to Professor Dilip Angom, Professor Krishna Kumar, Professor Safwan, and Professor Manson for their contribution in one of the first meetings, which was mentioned again and again here, that happened on 20th March 2019. Their specific recommendations in that meeting helped us to constitute the required framework that finally led to be the formation of the center. In addition, the center is lucky to have a very good group of scientists from this area as adjunct members. Among them, Dr. Kaushik Saha from IIT Dharwad, Dr. Jobin Jose from IIT Patna, Dr. Rajesh Kushawahab from PRL. They are with us now, and they have expressed their aspirations in this meeting. I thank you all for your time and involvement with the center. Well, the heart and soul of the center is, of course, the principal investigators, the PIs, our young and enthusiastic scientists. So they actually constitute the center and will take it forward along the lines of its proposed objectives. The PIs include 10 faculty members from IIT Tirupati and 5 from IISER Tirupati. Among them, I would like to specially mention Dr. Arijit Sharma and Dr. Sunil Kumar, who talked to us briefly today as program coordinators representing both institutions, and Professor Kodeshwar Rao, Chair of Physics, IIT. I thank you all for your active participation and wish you all the very best in your research activities as part of the center. This beautiful video documentary on CAMOST that we all watch now is produced by Sri Kannan Krishnamurthy from NPTEL IIT Chennai. I thank him for the time and the efforts that he has put in, and all the others who collected and provided the material for the video within such a short time. Now, the academic leadership at both institutes, IIT Tirupati and IISER Tirupati, the deans and chairs and the administrative leadership, especially members of the board of governors of both the institutes, need special mention, and they are acknowledged greatly for their generous support here. And as mentioned earlier, many faculty and staff at IIT and IISER have helped in conducting the various conferences and meetings prior to this inauguration today. It's difficult to list all the names, but on behalf of the center, I thank all of them for their support at various stages. For organizing today's function, the admin and IT sections at ISER and IIT have been a great help. On behalf of all of us, I thank all of them, especially Srikanth, Ravi, Arun, and Devi Prasanthi for their technical support for this function. I wish the center all the very best. As a joint initiative of two premier institutes in Tirupati, it had an excellent start. Thank you all.
Thank you, Professor Ambika. I noticed from the conversation in the chat box that it was suggested that Professor Manson leaves the meeting and rejoins if he could. But I noticed that he left the meeting, but I have not noticed that he has rejoined. So
I have.
Oh yeah, wonderful. Yes, Steve, you're on. So
you can actually hear me now?
Yes, absolutely. Please go ahead. We do not see you. We do not see you, but we hear you. So please, wonderful to have you with us, Steve.
It says my camera is on, but it said that for a long time anyway. I'm honored to be here. I'm delighted that this has finally come off. I've been involved with atomic physics in India for a little bit more than 30 years now, and I've watched it grow. And a crucial thing that has been mentioned time and time again during this meeting is the idea of collaboration. You know, I embody it. I have collaborated with many of you, as you know, over the years, and I find that far from being nurturing, I have been nurtured by this. It has helped me enormously to have collaborated with so many of you. Now, this formation of this center is merely a how shall I put it, a recognition of what is going on in India and a focus. And one of the nicest things about physics is it doesn't matter who says it. What matters is what's right. There is, well, I shouldn't say no politics, but there's relatively little politics in science, particularly in physics. And I like that very much. I remember years ago when I sent a manuscript to my former postdoc advisor, Ugo Fano. Some of you might have known him. And I got a note back from him giving his opinion of his manuscript, the opinion of his postdoc, and the opinion of a first-year graduate student at the time, who some of you may know. He was Indian. His name is Ravi Rao. And that always impressed me, because his point was, it didn't matter who says it. It mattered what was right. Look at that. Keep that in mind and go forward. And I know this will be a success because it is already a success. It is really a recognition. The formation of this institute is really a recognition of the success of atomic physics in India. So congratulations to all of you. Thank you.
Thank you very much, Steve. That pretty much brings us to the end of this meeting. Certainly, all the members of the Scientific Advisory Council, we look for an opportunity to have you at Tirupati sometime soon. We will, in the meantime, we will try to have you on various webinars, workshops, conferences, and so on. So we will continue to interact and benefit from you, but certainly look forward to have you with us. So maybe if I may request Professor Satyanarayana to close this meeting, make a few comments, and then close this meeting.
Thank you, Pranav. So as it's a real proud moment for both our institutions that we were able to bring all of you together and get this center started off. And I hope, you know, as Professor Arvind had pointed out, there are a number of missions that are starting at the national level. which we should. I wish we are. I hope we are going to be one of the hubs that he talked about in the quantum mission, and similarly in other initiatives that come forward. And we have very young, enthusiastic team. So all our support will be there for them, and with the able guidance of a lot of the scientists we see here, and you know. The fact that you were able to bring many of them to the institute, both our institutes, and then give their blessings, saying that you should go forward. Whether it's Professor Krishna Kumar and everyone, Dilip and Steve, Dr. Ravindra Kumar and Professor Safwan, right? Many of them have, you know, when I saw this kind of support, I said we should throw weight behind it and make it happen. And I'm very glad it's happened. And so this is a start. We have a long way to go, and let's make it a big success. Thank you very much.
Okay, thank you very much, and goodbye, everybody. We may all sign off, I guess. Thank you very much. Goodbye.
Goodbye. Thank you.
All the best. Take care.
Bye. Bye. Goodbye.
Goodbye.